welcome all the students who are appearing for the IIT JEE and the NEET examinations. So I wish each and every one of you all the best on behalf of myself and on behalf of all the faculty members and technical staff of AHA Guru. So all the best. As a sample session, I will be starting today the elimination reaction towards the preparation of alkenes. You know, alkenes, there are different methods. Of the general methods of preparation of alkenes, there are different starting points. General methods of preparation of alkenes, that should be the heading. And one of the reactions is going to be elimination reaction. Now, we know reactions are classified as 4 major reactions: substitution reaction, elimination reaction, addition reaction, and finally rearrangement. And each one of these reactions is further classified under 3 headings. Mechanism, in terms of the mechanism, we are going to concentrate on the mechanism. Each one of them can be classified into electrophilic addition, depending on the nature of the reagent. Electrophilic addition mechanism, and it could be nucleophilic substitution or addition, nucleophilic addition reaction, and free radical addition. And therefore 4 into 3, 12 types of mechanisms we will be seeing, and that is free radical reaction. Sorry, it's a free radical reactions: electrophilic substitution, nucleophilic substitution reaction, free radical substitution reaction. Based on the nature of the reagent, here the reagent is going to be an electrophile, electron deficient compound. Here this is going to be a nucleophile, electron rich species, and this is going to be a dot, free radicals. Okay, right. Now, elimination reaction, as the name itself suggests, a simple molecules like water, alcohol, or hydrogen halide, or it could be, for that matter, even hydrogen minus H2. Hydrogen can be removed, and we have specific name for these reactions: hydrogen, and it could be halogens, and this is called dehydration, and this is called dehydrohalogenation reaction, dehydrogenation reaction, and dehalogenation reactions. And probably we will be explaining all these methods also towards the preparation of an alkene. Okay, let us take the simplest reaction, namely dehydrohalogenation reaction, subtopic for you, dehydrohalogenation. Dehydrohalogenation reaction, as the name itself suggests, we are going to remove a molecule of HX here, hydrogen halide. Okay, right. Now, let's see how an alkane can be prepared by this process. The simplest alkane that I can take care of is CH3, CH2, chloroethane, ethyl chloride. And what should I do? I should remove a molecule of HCl to form CH2 double bond CH2. Therefore, that could be one of the questions. Identify haloalkane which cannot be used to prepare the alkene. You need to have minimum 2 carbon atoms to have a double bond. So, I cannot use methyl chloride. So, they will give you different examples, and this cannot be used for the preparation of, I cannot remove a molecule of HCl to put a double bond here. And elimination reactions can be again be classified into elimination reactions, types of elimination reactions, types of elimination reaction, types of elimination reaction. It could be alpha elimination, beta elimination, gamma elimination, delta. If it is going to be, and alpha elimination, I am removing a molecule of HCl from the same carbon atom, alpha carbon atom, and the beta. There are examples, but the most important prominent one is going to be beta elimination. That is, the hydrogen halide is removed from the for example, I have, what is beta elimination? It could be anywhere, not necessarily the terminal carbon atom. The halogen can be in the non-terminal carbon atom. And what do you call that carbon containing the alpha hydrogen halogen here? This is called alpha carbon, beta carbon, gamma, delta, epsilon. It goes like that. So, if a hydrogen, depending on the hydrogen, whether it is going to be alpha hydrogen or beta hydrogen, it's a beta hydrogen atom. So, halogen is removed from the alpha carbon atom and hydrogen is removed from the beta carbon atom. That kind of elimination is called the beta elimination, and that is going to give you a double bond, alkene. And we also have examples here, but very rare here, and it is going to give you unstable species. What happens if you are going to remove H and hydrogen and chlorine from the same carbon atom? You end up with CH3CH, and that is going to be a carbene. That is going to be a carbene. Of course, carbene being unstable, it should rearrange to form the final product here. And what should be a gamma elimination here? The halogen from the this is the alpha carbon atom. I may have carbon on this side also, alpha carbon atom, and this is the beta carbon atom, and this is the gamma carbon atom. If the hydrogen from this and halogen from this is called gamma elimination. And the gamma elimination, delta elimination, epsilon elimination, omega elimination should give you cyclic compounds. I have a hydrogen on the 6th carbon atom and chlorine on the 1st carbon atom. I am not going to fuse the 1st and the 6th carbon atom to form cyclohexane. So, that is called the omega elimination. Depending on the position of the hydrogen atom, we classify them as alpha, beta, gamma elimination reactions. Okay. The next one, in terms of the mechanism, what are the different types of classification of elimination reaction? Classification or types of elimination reaction, or classification of elimination reaction. Now, we have got, they are identified as E1 reaction, E2 reaction, and in NCERT level you have to learn only E1 and E2 here, and at a higher level you have to learn, one has to learn E1 CB mechanism, E1 CB mechanism. These are the different types of mechanism that one has to learn, and questions are going to be based on this type. That is what we are going to do today. E1 reaction, expansion of E1 reaction, elimination unimolecular. A is called elimination unimolecular reaction. Unimolecular reaction. Molecularity is 1. The numbers indicate the molecularity. Molecularity is 1. And obviously, this is A, this is B, and this is C. The expansion of E2, elimination bimolecular reaction. Elimination bimolecular reaction. C. Elimination, 1 stands for molecularity 1, unimolecular, and C stands for conjugate base. Conjugate base. A few reactions go by E1CB mechanism. It's so called, anyhow, I am going to explain to you towards the end here. It's a conjugate base because I am going to generate a carbanion as an intermediate. Carbanion is a base, isn't it? It's a conjugate base of what? Conjugate base of an alkane, RH. And that can give rise to R minus. That is going to be an intermediate. You have different intermediates here. And we have got evidences also. And how each one selects the mechanism depends on the nature of the substrate, nature of the reagent, and condition, various other conditions. Okay. Now, of the three, the most common mechanism, most of the reactions, elimination reactions, go by E2 mechanism. Let's see the major difference between E1, E2, and E1CB. And E2 is the simplest reaction, and that goes by a single step process. And others, namely E1 reaction as well as E1CB mechanism, they go by multi-step process. Now, what is the major difference between a single step process and the multi-step process? It goes by the intermediate. There is an intermediate form here. No intermediate is produced. No intermediate here. There is no intermediate here. No intermediate. Now, how does your potential energy diagram look like? Let's say it is going to be endothermic process. Alkyl halide given to an alkene. Let's say alkyl halide is converted into an alkene using a reagent here. Now, in the case of E2 reaction, your potential energy diagram, this is your reactant here, this is your alkyl halide here, this is alkyl halide, and alkene, let's assume it's going to be endothermic process. My dear students, please note, most of the alkane reactions are done at higher temperature, on heating only. That's the major difference between a substitution reaction and elimination reaction. Elimination reactions, most of them are done on heating. We have an explanation also for that. Alkene, therefore, this is an endothermic process, therefore it goes over there, and this is your transition state, alkene here. Whereas in the case of E1 reaction, let me write how does it look like. If it is a two-step process, you should have one intermediate and two transition states. For example, how does your E1 reaction go? Alkyl halide is converted to intermediate now, and intermediate is converted into an alkene. Assume that it is going to be a two-step process here. And in this case, we are going to propose the formation of carbocation. As we have proposed a carbanion in the case of E1CB mechanism, it should be a carbocation produced here. What is the type of intermediate in E2 reaction? What is the type of intermediate? There is no intermediate there. It's a single step process. Single step. That they could ask you the type of intermediate in E2 reaction is a carbocation, carbanion, free radical, none of the above. The answer is none of the above. Therefore, this is going to be a two-step process, and let us say overall reaction delta H is equal to. They will give you all the informations. The overall reaction is exothermic or endothermic, and they will give you 4 different potential energy diagrams you are asked to identify. Now, in this case, the first step can be a rate determining step. Second step obviously is going to be the fastest step. Now, what happens here? How does it look like? It's an endothermic reaction. I have an alkyl halide, and intermediate, definitely it is here, and it has got very high activation energy, therefore it is a rate determining step. The second step can be exothermic process. The first step is endothermic process. Second step can be exothermic reaction. But the overall reaction, you have an alkene here. I can generate as many questions as possible using this diagram here. I can ask you what is going to be delta H for each step here. Delta H is positive and positive. Delta H is negative and negative here. Positive, negative, negative, positive here. And this is going to be, what should be the answer now? Delta H is positive with the first step formation of the intermediate here, and negative in the case of the product here. And overall reaction, I can still ask you the overall reaction, delta H is positive or delta H is negative. Delta H is positive here. And why should this be rate determining step here? And I can definitely give you one more step, incorrect answer here. Now look at this. This is alkyl halide, and this is your intermediate here, and your product is here. Product is here. I can give you this particular. This is your. Now look at this. In this particular diagram, second step happens to be rate determining step, but actually it is not the rate determining step. It is incorrect. Because how do you say, look at the rate determining step by looking at the diagram, the one which has got very high activation energy, isn't it? Look at this. What is the activation energy? This particular distance here. This is what is known as activated complex or transition state. Now the potential energy difference between the starting material and activation, that is called E act. That is called E act. Now what is the activation energy in the second step here? Look at this, which is taller here. The second mountain is taller here. Therefore, that if the second step, that is the rate determining step. The step which has got higher activation energy must be the rate determining step here. Therefore, in this diagram, the second step is rate determining step, but the mechanism tells you the first step is the rate determining step. Can this be the answer for this particular question here? No, it cannot. Therefore, the answer is A. So they can give you 4 options here in terms of the potential energy diagram. Is that clear to you? And that could be one question here. So in the case of multi-step process, it's a multi-step process because you are getting an intermediate. And intermediate, we have to isolate that intermediate or prove the formation of the intermediate. It can be isolated or it can be inferred. Okay, when do you infer it? When do you isolate it, intermediate? When do you isolate an intermediate? When do you infer an intermediate? If isolate is very stable, it is going to be formed during the course of the reaction. Stop the reaction and try to get it, purify this, put it in a bottle, keep it for a day, a week, a month, and a year, and continue the process. That is an intermediate. That is isolable. When is it isolable? If it is going to be very stable. Now some intermediates are going to be highly unstable. Highly unstable. They form. How does your potential, I can indicate it in the case of potential energy diagram. Look at this. This is going to be an intermediate here, and this is going to be the product. Look at this. Now from this itself, we can prove that intermediate is highly reactive. Why is it highly reactive? Look at the activation energy here. Look at the activation energy here. It's so small. For any reaction, if the activation energy is so small, it's a spontaneous reaction. Have you not seen it in the case of supplying one spark for the Indian gas? One spark. How does your potential energy diagram for that? It's almost on the top of it. Almost on the top of it. Potential energy. Activation energy is so small. That is why we need just a spark for the Indian gas to catch fire. Isn't it? So from the diagram also, I can get the nature of the intermediate, whether it's stable, isolable intermediate, or it is that can only be inferred. Now in this case, it can only be inferred because it is so reactive. By the time you stop the reaction, isolate it, it would have converted into the product. But are we not supposed to prove the presence, formation of this? Now we seek the help of the modern gadgets. Spectroscopic techniques. We have different spectroscopy. We have UV spectroscopy, ultraviolet spectroscopy. We have IR infrared spectroscopy, NMR, nuclear magnetic resonance spectroscopy. We have got mass spectroscopy. These are the various gadgets available now modern days to infer even for the lifetime. Supposing the intermediate is going to stay only for a fraction of a picosecond. Let it be a fraction of a picosecond. The moment it is formed, it is recorded over there. And that can be taken as an evidence. That can be taken as evidence. And that way we prove that particular reaction is not an E2 reaction. Because we have at least identified the formation of intermediate. So whenever intermediate is formed, it is not a single step process, it's a multi-step process. That how do I know whether it's E1CP mechanism? and E1 mechanism, both of them are two-step here. We have to go for some other technique evidence. We only prove at this stage it is not an E2 mechanism. Is that clear to you? So that could be one question here. So that is the type of the intermediate E1 reaction and elimination reaction. Okay, and we will come back to the E1 CB later on. Even E1 also I am going to explain in detail, giving you lot more information about the E1 reaction. I just told you about the types of elimination reaction depending on the number of steps taking part in the reaction. Okay, now we shall take up in detail exhaustively E2 reaction. E2 elimination. I told you E is elimination and 2 is a molecularity, and we shall explain all those definitions also, molecularity. Now let me write the reaction. What is the reaction? Alkyl halide. I use the reagent alcoholic base. I get an alkene. The alcoholic base could be alcoholic NaOH, alcoholic KOH, alcoholic sodamide NaH2, or it could be sodium alkoxide. Sodium alkoxide dissolved in alcohol, all of them dissolved in alcohol. Aqueous KOH dissolved in water. It is soluble both in alcohol and this. And we are not supposed to use aqueous KOH here for this particular reaction. The product is going to be a different product. The mechanism is going to be different. Route is going to be different. Terminal point is going to be different. Now, what is the terminal point here? You end up with the formation of an alcohol. Look at this. I don't want alcohol. If we are going to use aqueous KOH on ROH here, I end up with an alcohol. And what should be the other product? Potassium halide. The mechanism itself is different, isn't it? And what is that I am going to get here? I will be getting potassium halide plus water. Potassium halide plus water. The mechanism itself is different. It's an elimination reaction, whereas this is the substitution reaction. Substitution reaction. The simple questions of this type can be asked in the main examination. Substitution reaction, whether it's the nucleophilic substitution or free radical substitution or electrophilic substitution. And what is that is decided by the nature of the reagent. What is the reagent here? Nucleophile. Therefore, this is an example of SN reaction, substitution nucleophilic or nucleophilic substitution reaction. Therefore, the nature of if you change the solvent, the entire mechanistic course is completely altered. Now, I have to explain to you how an alcoholic KOH is used in the elimination reaction and not aqueous KOH here. Now, the OH minus ion is the reagent here. This is the substrate. I used two different solvents. One, water. The other one, alcohol. In aqueous KOH, it is used as a nucleophile. This is used as a base, isn't it? Previously, we learned why in the presence of water it acts as a nucleophile. Why in the presence of an alcohol it acts as a base? First of all, tell me what is the major difference between the nucleophile and the base? Nucleophiles are electron donors. They have the ability to donate a pair of electrons. A base accepts a proton. Though you have the same electron pair there, it is not able to donate because it is more tightly attached to the reagent. If electrons are tightly attached to the reagent, it will not be able to donate a pair of electrons. It has only the capacity to accept a proton. Acceptance of proton, Bronsted base, proton acceptor. Now, what happens here? By using water here, the electrons are slowly removed away from the oxygen atom, is go far away. When the electrons come far away from the oxygen atom, then it has the ability to donate a pair of electrons. Then it access. Now, how does it happen here? Maybe because of this OH minus ion, it is going to be solvated, more readily solvated in the presence of water. This is an aqueous condition here, more readily solvated. It is not so. It is not so, because water is a more polar solvent. More polar solvent. This is the less polar solvent, excepting methanol probably. Alcohol generally we use, alcohol means ethanol only we use. Now, what happens here? It's easy for me to understand if you are going to take a polar solvent and non-polar solvent. In the case of a polar solvent, let me take a polar solvent water. Let me take a non-polar solvent carbon disulfide or carbon tetrachloride. Now, what happens? In the case of this, the reagent, what is the reagent here? OH minus ion is solvated. There is going to be attraction towards this. What kind of attraction here? It could be ion dipole attraction, or it could be hydrogen bonded attraction. That could be another question for you. The type of attraction, kind of attraction between the OH minus ion, this is the hydroxide group here. This is the OH group here, and surrounded by this. The type of attraction between, make a note of it. This is going to be the type of attraction between the OH minus ion and water. Ion attraction, ion dipole attraction. Ion dipole attraction or hydrogen bonded attraction here. So, with the result, what happened? The volume of that particular reagent, the solvated ion, increases, bulges out. So, in this process, what about? The electrons come to the surface, far away from the oxygen atom. Now, it has the ability to donate a pair of electrons. It is going to act as a nucleophile. And what should happen in the case of this? This is simply, there is no solvation at all. There is no solvation at all. And this can be represented as non-solvated OH minus ion. Non-solvated. And the electrons are, this is going to be the volume of the non-solvated OH minus ion. The electrons are found much closer to the oxygen atom. Oxygen by nature is going to be highly electronegative, isn't it? Therefore, it is going to hold that pair of electron density towards itself, and the ability to donate an electron is going to be negligible. Okay. If that is so, I have another question. Why do I go only by less polar solvent? I could have the basic properties enhanced in the non-polar solvent. I could have used the reaction OH minus sodium hydroxide and carbon disulfide. We have no reaction. Why is it so? Sodium hydroxide is insoluble in carbon disulfide. Sodium hydroxide is a solid. It is insoluble. Can you dissolve sodium chloride in kerosene? Can you dissolve sodium chloride in petrol? No. Same way, sodium hydroxide being an ionic compound, it must be insoluble. And if you don't have a reaction here, and there is no collision, I told you. What is the job of the solvent here? It acts as a platform for the reaction, isn't it? Medium for the reaction. Therefore, it is not soluble in carbon disulfide or carbon tetrachloride. Therefore, there is no reaction here. And probably that is why we want to use definitely a polar solvent, but definitely much less polar solvent than water. In this case, it acts as a base, and here it acts as a nucleophile. Therefore, now we shall see how exactly we have to visualize. Visualization of the reaction is the step-by-step description of a reaction. That is called a mechanism of a reaction. Visualization of reaction. Now, for that, we need to know structural requirement. We have already seen the type of reagent, alcoholic KOH. Structural requirement of haloalkenes. What should be the structural requirement of an haloalkane? I need to have halide, definitely alkyl halide. I need to have at least one beta hydrogen atom. There must be one beta hydrogen atom. For what reaction to take place? For beta elimination to take place. Beta elimination. If there is no, which of the following, that I could generate one more question. Which of the following cannot undergo beta elimination? The one which does not contain the beta hydrogen atom. The hydrogen atom could be substituted by methyl group here, methyl group here, methyl group here. And of course, you can have alpha hydrogen atom. Alpha hydrogen atom, presence or absence of alpha hydrogen atom is no criterion for me. I need to have. And this beta elimination, the beta elimination, you have another name. What is the other name for this? It is also known as 1,2 elimination. 1,2 elimination. Most of the reaction take place in the 1,2 elimination. Halogen on the carbon 1 and the hydrogen on the next carbon atom. It can be terminal carbon atom, it could be middle carbon atom. Alpha carbon atom is considered as carbon 1 for the sake of convenience, but in terms, not in terms of IUPAC nomenclature. Do you consider this as a carbon 1 here? Chloropropane? Definitely not. It is called 2-chloropropane only, isn't it? But for the sake of our mechanism here, I consider this as a carbon 1 and these two are carbon 2. Only then it is called 1,2 elimination. 1,2 elimination. Okay? When I say carbon 1, it is the alpha carbon atom. Alpha carbon atom. This is the structural requirement. This is the structural requirement for this. That is, number 1, it should contain, what should be the nature of the X here? Can this always be halogen here? Not necessarily. The halogen, what is the nature of X here? Nature of X can be halide. It could be fluoride, chloride, bromide, iodide. It could be a fluorine, chlorine, bromine, and iodine. Hex. Hex is the leaving group here. X is the leaving group. It is not the halide here. Generally, we write X as for the halide here. X is the leaving group here. Okay. The next one, it could also be OH2, H2O, OH. It could also be NH2, NH2, any group, any group. It could be OMe, OMe, any functional group. It could be SO3H. And on the whole, what is the name given to that? It should have a good leaving group. Another important condition, good leaving group, which I have not mentioned in the previous class. Good leaving group. The best leaving group, of course, the reaction has to be done in acid medium. All these reactions to be done in acid medium. That could be another condition. If you have X here in the form of OH, in the form of NH2, if it is NH2, what do you call that? Alkane amine. If X is equal to NH2, alkane amine. If X is equal to OH, alcohol. If X is equal to chlorine, bromine, and iodine, and alkyl haloalkane. If X is equal to OR, alkoxy alkane, ethers. But they are very poor leaving group as such, the OH minus ion. Whereas what happens here? I have to do it in the presence of basic acidic condition. These compounds generally become a good leaving group in the presence of acidic condition. What happens when you add H plus to the OH minus ion? It is converted into OH2 plus. It's already attached to the carbon atom. You remember the OH is converted to OH2. And what happens? NH2, if X is equal to NH2 in the alkaline acidic medium, it is converted into NH3 plus. Should you not put a bond there? Yes. Dash NH2 in alkaline acidic medium, it is converted to NH3 plus. And what should happen in the case of the alcohol, OMe? It is converted into OMeH, alcohol. Why do you want to do it? Because they become a good leaving group now. When you compare water and OH minus ion, water is a poor leaving group. Sorry, OH minus ion is a poor leaving group. Water is a good leaving group. I shall explain. Leaving group ability also. Factors, there are different factors explaining the leaving group ability also. A group wants to go on its own, spontaneously. It's considered as the best leaving group. Best leaving group that we were considering, probably we'll be thinking in terms of N2. Whenever nitrogen goes off, whenever carbon dioxide goes off, decarboxylation. Now, this is going to be, that's the reason why we want to add H plus here, because it's reluctant to go out. It is tightly attached to the carbon atom. Now I am giving you the explanation. It is tightly attached to the carbon atom. If the bond dissociation enthalpy of carbon halogen bond, what is that X here? It's not the halogen only, it's a leaving group. It could be halogen or any one of them. If the bond is very strong, it's very difficult for that to go. And what should happen here? Am I not going to remove H here and halogen here? Dehydrohalogenation reaction. For H and OH, dehydration. Therefore, what should I do? I have to add H plus here. And the moment I am going to add OH, and this is converted into, in one case I got the OH, in another case I got OH2. Now you know the explanation. By adding a proton here, I have a positive charge. The positive charge in the carbon oxygen atom makes this bond weaker. Automatically, the bond dissociation enthalpy between the carbon and this oxygen atom becomes weaker. And this is one of the ways of weakening the bond by protonation, generally by protonation. So the immediate adjacent bond becomes weaker. Why? Because this is an electron withdrawing minus I group, isn't it? Minus I, any minus I group will make that particular bond weaker. Okay, polar also, more polar. Okay, that apart. So one of the important conditions, it should have a leaving group, not simply a leaving group here, a good leaving group. That is the primary condition for an elimination reaction, and good leaving group. Good leaving group. And the second condition, what is the second condition here? Obviously, I need to have a beta hydrogen. A beta hydrogen, hydrogen attached to the beta carbon atom, hydrogen attached to a beta carbon atom is a hydrogen. And that is going to be 1,2 elimination. And 1,2 elimination only you put the carbon-carbon double bond. Are we not discussing general methods of preparation of alkene? Yes. So we need to have 1,2 elimination. And what should be the nature of the hydrogen also here? What should be the nature of hydrogen? It should be fairly acidic in nature. Why should it be acidic? Because it is going to be abstracted by a proton. Now we shall see. When you see the mechanism, you will also know the why in some cases the reaction is going to be a single step process spontaneously, why in some other cases the reaction goes by stepwise process. In other words, why in some cases the reaction goes by E2 mechanism, the other one is E1 mechanism. Look at this. Probably you will be able to appreciate the nature of the beta hydrogen atom if you look at the mechanism. Write the mechanism. Mechanism of E2 reaction. Mechanism of what I am writing is E2 mechanism. I have hydrogen here. I am not worried. I may have more than one or more hydrogen atom, but definitely one beta hydrogen atom. And I don't need to have, I may not have hydrogen here. It could be an alkyl group. It could be an alkyl group. How do I classify the halide here? Supposing I have got two hydrogen atoms. And what do you call the halide if I got one hydrogen atom and one alkyl group? And what do you call the halide if you have two alkyl groups here? It's classified as primary, secondary and tertiary. The reactivity depends not only on the hydrogen atom, not only on the nature of the halogen here, it depends on the nature of presence or absence of alkyl group on which carbon atom? Alpha carbon atom. That's another condition. Definitely there is a difference in the rate of the reaction. Is that clear? We shall come back to that. So generally, how does it happen here? Now, I got the OH minus ion. Let's say I put the OH minus ion. Let me write this reaction here. And OH minus, I am very definite. I want to do the elimination reaction. So should I take aqueous KOH or alcoholic KOH? I have to take alcoholic KOH only. And what should happen? The OH minus, I think I have already told you, the primary property of OH minus ion is a base. Isn't it? Primary property. Because normally it is reluctant to donate a pair of electrons. Why? Oxygen is more electronegative. So the primary property is only to accept a proton. If the basic property is suppressed, the nucleophilic property is enhanced. That is what we have done. How did you suppress the basic property? By adding water, by solvation. We are slowly removing the electrons away from the oxygen atom. Good. And as a base, what should it do? It is going to accept a proton. Of course, it is going to come there. it should be a direct 180 degrees attack. The OH minus ion, the hydrogen, the carbon should be linear. Only then the collision, if it is going to attack the hydrogen ion, the impact is going to be much greater and the bond is going to be cleaved. Okay? Not when it is going to attack at 90 degrees, 0 degrees. No, it should be 180 degrees apart. 180 degrees apart. It is going to attack. So it is going to abstract here, and the single bond that you have can be converted into a double bond. You have to, this is what we are visualizing, and I can generate dozens of questions based on this visualization. And that is what is asked in IIT question, advanced question and the main examination question. Now, valency becomes, if you put a double bond here, the valency becomes 5 here. Therefore, automatically, already the halogen is prepared to, waiting for an opportunity to come out. It's a good leaving group. It being supported by that push. You are prepared to go, and you are being pushed. Okay? And that is what is happening. And anything which is supported by a neighbor, any reactant supported by a neighbor, it is said to have neighboring group effect. Neighboring group effect. We are going to discuss elaborately on this neighboring group effect. It is also known as ankymeric assistance effect. Ankymeric effect or ankymeric assistance helps supported by a neighbor. Generally by dictionary meaning neighbor is supposed to help you, only then he is called a neighbor. So it helps in the formation of an alkene. Therefore, we will come back to this. So it is going to approach the hydrogen atom, and because of the collision the bond becomes weaker. It's not going to break just like that. This is going to be the bond initially, the carbon hydrogen bond. When it is going to come and pull the hydrogen atom, the bond becomes longer. The bond becomes longer and longer and longer. At one particular stage it snaps. Therefore it breaks. And what happened? Your oxygen hydrogen bond, this is your oxygen atom. The OH group here, there is no attraction. But definitely it comes here and there is going to be a formation of weak bond. So the bond becomes stronger and stronger. When the bond length of hydrogen atom and the oxygen atom is equal to that of water, the other bond is completely broken. This is what we have to visualize. We have OH here. It comes and approaches. It's going to take away the alpha hydrogen, beta hydrogen, isn't it? So the bond becomes stronger and stronger. The distance decreases. At what point the other bond, the hydrogen atom and the beta carbon atom is going to snap here? When the bond distance between the oxygen and the hydrogen is equal to that of water. At that stage, it's going to snap. Now, at that stage, what are the other changes you visualize in the case of the molecule? Tell me. What are the other bond? So, this bond becomes longer and longer. Why? The bond should become weaker and weaker. We know longer the bond, weaker the bond. Our purpose, the aim is to break the bond. So, definitely we want to weaken the bond. Now, what should happen to the carbon-carbon distance here? Now, carbon-carbon distance also. So, all these things happen simultaneously. The oxygen is coming closer and closer. The carbon-hydrogen bond becomes longer and longer. Simultaneously, the carbon and carbon become shorter and shorter. Why should it become shorter and shorter? Because the bond distance in the case of a carbon-carbon double bond is less than that of a carbon-carbon single bond. Don't we know the particular distance here? The carbon-carbon single bond distance is equal to 154 picometers. 154 picometers. Carbon-carbon double bond. Tell me. 132 or 133 picometers. Carbon-carbon triple bond, 120 picometers. We know. Why should the bond distance become less as the bond multiplicity increases? because of the lateral overlap. For the lateral overlap to take place, no, the two atoms should come closer. Okay, we have come up to this. The carbon-carbon bond becomes double bond. And finally, it should reach 132 picometers or 133 picometers. When it becomes 132 picometers, the reaction is over. Product is produced. And what should happen? What should happen to this carbon-halogen bond? When it is doing all these things that are happening here, the carbon-halogen bond also becomes longer and longer and longer. At one particular stage, it is snapped, broken, and that comes out as. And what is going to happen here, during which process the halogen is going to withdraw the electron towards itself, because ultimately it has to go out as X minus. It has to go out as X minus. So all these things happen. One more thing is also happening, which I have not mentioned. Can you observe? Tell me. What else? I have told you oxygen-hydrogen bond becomes stronger and stronger. Okay. And this becomes longer and longer. This becomes shorter and shorter. Here it's going to be lateral overlap here because of the formation of pi bond here. And this is going to become longer and longer. I have told you all these things. One more thing is also happening to the molecule. What is that? In terms of the structure. In fact, that is what the mechanism, that is how the reaction molecule is going to take place. Planar, wonderful. Isn't it start with sp3 carbon atom? sp3 carbon atom, it is going to be converted into, let's say, this is going to be removed by OH minus ion. Let's come back here. This is the OH minus ion. So OH minus ion obstruct the beta hydrogen atom to form water. And what should happen to this? This becomes a carbon-carbon double bond and halogen goes out. This is the final product. And this is going to be an sp2 carbon atom. sp2 carbon atom, the entire molecule becomes planar. That is also yet another feature that is happening in the molecule. That could be a question here. So what do you want to explain here when the molecule becomes planar? Tell me. What should happen here? The bond angle. It was sp3. Now slowly what happened? It becomes, now you look at this. Isn't it? What should be the bond angle between the two hydrogen atoms? 120. So 109.5, and slowly when it comes here, let us visualize only the bond angle only. We have seen the visualization of how OH minus ion is going to approach here. Now visualize this. This is going to be 109.5. When that comes closer and closer, not only here, it comes planar here and it becomes 120. 120. Everything is happening. The whole thing is happening. And that is the mechanism. So what are the changes? Which of the following is not happening? Which of the following does not happen during the quotient? I can give you the formation of the oxygen hydrogen bond, that is correct, and the lengthening of carbon beta hydrogen bond and the formation of this. Everything is all right, excepting that the bond angle, there is a decrease in the bond angle at between the hydrogen atom at the alpha carbon atom and beta carbon atom. It is not the decrease in the bond angle, it is an increase in the bond angle. Make a note of it. Where does the increase take place? Which carbon atom? It happens only at the alpha carbon atom. It happens only at the beta carbon atom. It happens both at the alpha and the beta carbon atom. None of the above. What's your answer? Both alpha carbon atom, beta carbon. Another question. Another question. Another question. So the bond angle should increase between two hydrogen atom, any two hydrogen atom, from 109.5 to 120 at both the alpha and the beta carbon atom. Both the alpha and beta carbon atom. That is how a molecule should have undergone a reaction. That's how the molecule should have undergone reaction here. Step by step visualization, step by step description of a reaction, and that is called the mechanism. We have also seen the features, structural requirement of this. What is the structural requirement? It should contain a beta hydrogen atom, at least one beta hydrogen atom. And that should be moderately acidic in nature for the E2 reaction to take place. We are discussing the condition for the E2 reaction. The condition for the E1 reaction is different. The structural requirement for the E1 reaction is different. It should be moderately. Why it should be moderately? Simultaneously, both the bonds must break here. If the bond is very strong, much stronger than this bond, what happens? Only that goes, then it becomes a step-based process. And that is what is happening in E1 mechanism. E1 mechanism. It depends on how does the molecule decide whether it should go by E1 reaction or E2 reaction. all these parameters, all these parameters. Moderate bond, strong bond, not very strong, not very weak. If this bond is so weak, visualize the other way about. The bond is so weak when compared to this bond. Can you suggest one example where this bond is carbon and the leaving group is so strong? Carbon-fluorine bond. X happens to be fluorine. So you are not going to propose E2 mechanism, you are not going to propose E1 mechanism, you are going to propose E1CB mechanism. And I told you, no, there is a formation of carbanion. When does a carbanion form? When the hydrogen goes as H plus ion. So it mainly depends on this particular bond association enthalpy, whether it is going to be E1 reaction or E2 reaction or E1CB mechanism. When it is very strong, halogen goes out. When the halogen goes out, are you not going to propose a carbocation here? Are you not proposing a carbocation? Yes. Now that is going to be E1 mechanism. When this is going to be very weak, very weak when compared to the carbon halogen bond, it allows the hydrogen to go out as H plus ion, a carbanion. So carbanion intermediate, what is the mechanism? E1CB mechanism. And when they are going to be more or less equivalent, moderate, then E2 mechanism, simultaneous. That could be another question based on this. The nature of the bond dissociation enthalpy with the beta hydrogen. Nature of the bond dissociation enthalpy with the beta hydrogen atom. Okay. Now, we have to give evidences for the mechanism. We are in the evidences. And for that we should know the features of E2 reaction. What is happening? Number one, it's a single step process. Single step process. So what? What is the use of single step process? What is the use of single step process? I know everything. That is why it is called a single step. Whenever there is no intermediate, it's a single step process. Should that be the answer for this question? What is the significance of the single step process? Excellent yield. Make a note of it. Excellent yield. Good yield. As a rule of thumb, general rule, whenever you are asked to synthesize any compound, it should be as far as possible single step process. The yield is going to be much greater. The yield is going to be reduced in the case of multi-step process. In a two-step process, as the number of steps increases, the yield is also proportionately reduced. Why is it so? Because all the reactions are not 100% reactions. Let's say the reactant R is converted to the product. It's a single step process. It is going to be 80% yield conversion. When do you call this as quantitative reaction if it is going to be 100% yield? Very few reactions are quantitative reaction in organic chemistry. Most of the ionic reactions, inorganic reactions are quantitative reactions. If I ask you to give one example, the common example that should come to your mind immediately is take sodium chloride, add silver nitrate, immediate formation of cloudy white precipitate, the ionic reaction. Why? Ag plus ion immediately combine with Cl minus to form a precipitate because it's going to be highly stable. Very high lattice energy, that is why it is insoluble, isn't it? Silver chloride is insoluble. Spontaneous reaction. And wherever you get 100% yield, theoretical process and the experimental process agree, then it is called quantitative reaction. That is why those analyses which you do in the laboratory, wherever you have 100% conversion, is called quantitative reactions. You do two types of quantitative reaction. Now, in the 12th standard, you do volumetric analysis. Volumetric analysis is a quantitative reaction. Based on the normality, are you not going to calculate V1, N1 is equal to V2, N2? How can you do it if it is not going to be 100% conversion? We assume it is going to be 100% conversion, then we say V1 N1 is equal to V2 N2. Isn't it volumetric analysis for you? Number of milli-equivalents of an acid is equal to number of milli-equivalents of base. So that such reactions are called quantitative reaction, and one such example in quantitative reaction is volumetric analysis. The other one is called gravimetric analysis, based on the weight. One is called quantitative yield, should again be classified into quantitative yield, 100% yield, quantitative reactions. I am just giving you additional features as and when it is needed. Of course, not connected to necessary here. Quantitative reactions. It could again be volumetric analysis, and gravimetric analysis. Volumetric based on the volumes of the reacting substances, based on the weight of the reacting substances. You calculate the weight. Sodium chloride, I will give you one example, simple gravimetric analysis here. You are given a solution of sodium chloride, some volume, 10 ml, each one of you, 10 ml, 10.2 ml, 11.1 ml, 5 ml, etc. You are asked to find out the amount of sodium chloride present in that. How do you do it? Would you evaporate that and find the weight here? During the evaporation, it might spurt out and some of it might be lost. That's not the way. So whatever substance sample you are given here, you take it here and add excess of silver chloride, silver nitrate. It was pure, 100% pure, it must be 100% pure. Silver nitrate solution. What happens when you add acrid? Everything, all the chloride is going to be precipitated as silver chloride. Yet another IIT question asked earlier. Simple numerical problem. Problem also can be done based on this explanation. So you have added excess of silver nitrate. And what happens to your chloride here? It is completely precipitated as silver chloride. Even though you have added excess of nitrate, as long as the chloride is there, okay, if chloride is going to be completely converted to silver chloride, no further reaction. What do? Stop at that particular stage. Filter, precipitate and filtrate. What is a precipitate? I want you to be with me. Silver chloride in the filter paper, and the filtrate, I don't need the filtrate. So in the filter paper I got silver chloride here, okay, and then add, you have to wash it because it is contaminated silver nitrate. It is also contaminated with some sodium chloride there maybe, okay, no, sodium chloride has been completely converted. The only contaminant that is expected to be is silver nitrate. So wash it repeatedly with water and silver nitrate is soluble, completely removed. And what you have in the filter paper is going to be pure but contaminated with the moisture now. And that has to be dried at 100 to 105 degrees centigrade for a few minutes, say for 30 minutes or 40 minutes, etc. And we have a separate crucible for that. Okay. I have taken the weight of empty crucible earlier before I start the experiment. I have added that silver chloride precipitate into that. I have got silver chloride in that crucible there. It has been dried there. So what is the second weight here? Crucible plus silver chloride. Earlier weight is crucible alone. The difference in these two will give you weight of silver chloride. I don't need water. Weight of silver chloride. And from the weight of silver, let's say I have got W grams of weight of silver chloride is equal to, let's say, 100 grams. I get 100 grams of pure silver chloride. And isn't it possible for me to calculate the weight of sodium chloride? How do you do it? Molar ratio. 1 mole of sodium chloride should have given rise to 1 mole of silver chloride. What is the molecular weight of sodium chloride here? 58.5. 23 plus 35. What is the molecular weight? 108 plus 35.5. 108 plus 35. 143.5. So 143.5 grams of pure silver chloride should have been obtained from 58.5 grams. Therefore, 100 grams of silver chloride should have given rise to how much? So I have calculated this without evaporation, and that is called gravimetric method. Gravimetric is based on the weight. of the reacting substances. Volumetric method based on the volumes of the reacting. Okay, that apart, I wanted to tell you why did I start explaining all these things? Because organic reactions are not quantitative reactions. Organic reactions are not quantitative reactions. I get 80% yield. So whatever be the weight of it, 80% of it is going to be the product. Now I take a stepwise process. R is going to be converted to I1 here, I intermediate, and the intermediate is converted into a product. R is converted to I. This is 80% here, and let's say unfortunately this is 70% or 60%. It is much less. And what happens? 80% of this. And what should be the next step here? 70% of this is going to be still reduced. Upper majority of compound goes down the drain. So the final yield is going to be reduced. Final yield is going to be reduced. Final yield is going to be reduced. Therefore, and if the number of steps is going to be increased further, supposing I get 2 intermediates, the final yield is going to be. So, what is the conclusion here? Whenever you are asked to suggest, how would you prepare the following? You have got umpteen number of methods, A, B, C, D, E, F, and you have to suggest a method which has got the minimum number of steps. As far as possible, single step here. How do you know whether the reaction? And that is what we are learning now. From this, we should be able to understand whether it goes by a single step process or multi-step process. For that, one example, elimination reaction, E2 reaction. E2 reaction is a single step process. Excellent yield. That is one feature. See how many questions we are able to generate from based on the simple point over here. The next one. What is that you have to say? Single step process. And we have to explain the kinetics. I think I have told you last class itself. In this particular process, the whole process is a single step here, alkyl halide plus OH minus ion. I don't need to include water over here because that is the reagent. I don't need to include K plus ion. I don't need to include Na plus ion. Why? Because K plus ion and Na plus ion behave as spectator ions. In no way they are connected to the reaction here. They just simply stay there and watch the whole fun. Spectator ions. And the reagent that is actively participating is going to be the OH minus ion. Therefore, we have to include only the active mass, the molar concentration of the OH minus ion. And it is an alkene. You get an alkene. And plus alkyl halide ion. And plus H2O here. I don't need this product at all. In a kinetics here, I'm not interested in the product because I want to know the concentration, molar concentration of reacting substances. That is law of mass action. How can't you write this single step? It's the rate determining step. Okay, and you have to write the rate equation. I told you what is the rate equation. It's a relationship between the rate of the reaction and as per the law of mass action is direct. Assume that this is going to be a balanced equation, stoichiometric equation. 1 mole of this, 1 mole of OH minus ion. The rate of the reaction is directly proportional to the molar concentration, active mass to the power of 1 and the molar concentration of OH minus ion, OH minus ion to the power of 1. Therefore, I told you, I was explaining to you earlier, molecularity. I can also equate it also, introduce a proportionality constant. Rate is equal to K into active mass of alkyl halide to the power of 1 and active mass of OH minus ion to the power of 1. And the molecularity is some of the concentration terms present in the rate equation. Some of the concentration, this is going to be molecularity. The another term is going to be the order of a reaction. Now, this can be taken order of the reaction. The order of reaction. We have to prove that the reaction goes by E2 mechanism, and we have to. This is going to be the order. Order is equal to 2. It's a second order kinetics. E2 reaction. So kinetics. What do you want to write here? A. It follows second order kinetics. Second order reaction. Now, based on this equation, order is 8 is equal to active mass of Rx to the power of 1, OH minus ion to the power of sum of the powers of the concentration terms. 1 plus 1, 2. Order is equal to 2. order is equal to 2. And molecularity is also 2. These are the information. Molecularity is also equal to 2. Order is also equal to 2. And what is the molecularity? The number of species taking part in the rate determining step. I got alkyl halide plus OH minus ion. There are only 2 species over there, and therefore molecularity is 2. Bimolecular reaction. Bimolecular reaction. I told you another important information between molecularity and the order of the reaction. What did I tell you? Molecularity is a theoretical concept. Molecularity is a theoretical concept. Order is an experimental parameter. And you are going to learn it later on in chemical kinetics, how the order is determined in the laboratory by simple volumetric analysis. The order can be estimated, determined, and you do this reaction. For example, methyl iodide plus aqueous KOH. I'm sorry. It is a substitution reaction. Let me take ethyl iodide to form ethene. Let's say this is going to be the reaction here, plus potassium iodide and plus this. And we do this reaction. Of course, it's a gaseous substance. We have got lots of limitations. Assuming that we do the reaction, we find order is equal to 2. How can this be taken as an evidence? This is one of the features. And as per the mechanism here, this is the single step here, and that itself is the rate determining step. Therefore, the order is equal to 2. It tallies very well with the experimental results. Therefore, that can be taken as an evidence. Evidence is order. This is not an evidence. This is only a visualization. Is it possible for you to find the molecularity? No, you have to write the mechanism. From this information, I have no idea about the mechanism here, and this is going to be one of the evidences. Based on you collect all the evidences and prove that the reaction has to go this way, and find out based on this, if this were to be the mechanism, what should be the molecularity? Molecularity is 2. Order is also equal to molecularity is also equal to 2. Not necessarily. It could be different. It could be different. Okay? It could be different. And provided it is going to be a single step process. Elementary reactions, I told you. Elementary reactions or very simple reactions, not complex reactions. Okay? Whenever you get the intermediate here, that is not an elementary reaction, it's a complex reaction. Okay, that apart. This is going to be feature number 2. Feature number 2 can also be taken as evidence number 2. This is no evidence here. Can you take, what is the evidence you can do to prove that it's a single step process? Non-formation of intermediate by spectral technique, I told you. The intermediate need not be isolated, intermediate need not be inferred. If there is a 100% evidence that there is no evidence, there is no intermediate formed, if no intermediate is formed, if you are very definite about this, we have to come to a conclusion it is E2 reaction, single step process. And E2 reaction is a single step process. Okay. Feature number 3. Feature number 3. If any of these points not understood, please let me know. Feature number 3. Nature of X, leaving group. Nature of X. Let us assume this is going to be a halide, halogen. X is a halogen. X is a halogen. Apo, I have. How is Rx classified? RF, RCl, RBr, and RI. Should there be a difference in the rate of the reaction? In one case, I take fluoroethane, chloroethane, bromoethane, iodoethane. Would you expect a difference in the rate of reaction, or reactions are going to be identical, the same rate? And we have to see if that carbon halogen bond is broken, cleaved in the rate determining step. Is it cleaved in the rate determining step? Yes, obviously, because that single step. In that step, carbon halogen bond is broken. So, this carbon iodine bond is the weakest bond, carbon fluorine bond is the strongest bond, and it should take more energy to break this. And in fact, it is not E2 mechanism, I told you. If the fluorine carbon fluorine bond leaving group becomes more tightly attached to the carbon atom, alpha carbon atom, then you have formation of carbanion. It is converted to E1 Cp mechanism. Of course, there are reactions. In spite of it, the alpha beta hydrogen atom could be acidic. Now, assuming that fluoride also goes and hydrogen also goes by E2 mechanism, single step process, we have reactions. I will come back to that. But generally, it allows the substrate to be converted into carbanion. It goes by a different route. Therefore, what should be the reactivity? What should be the reactivity? Now tell me, that could be another very simple question for an NCERT as well as main examination. Alkyl iodide, reactivity of alkyl halide, alkyl iodide greater than alkyl bromide, alkyl chloride, alkyl fluoride. I can give you various permutation combination because we have already discussed this kind of variation among the halogens, isn't it? For a repetition, bond dissociation enthalpy, how does it change? Which bond is the strongest bond here? Chlorine bond greater than bromine bond greater than fluorine bond, iodine. Oh, the question has already come. Why does the yield reduce? Is it because you use some to get an intermediate? Oh, I didn't complete that particular process. I told you yield is excellent in a single step process. Maybe I should, okay, I have an alkyl halide, convert an intermediate I, and I have a product here. And let's say this is going to be 80% and this is going to be 70%. I start with 1 mole or W grams. Based on that, I calculate. Had it been 100%, based on the theoretical value, I calculate the molecular weight of methachloroethane. I calculate the molecular weight of this. If this is going to be converted to that 80 grams, whatever be the 80% of that particular weight, 1 mole, 80% of 1 mole, that should be the product. Now, second one is not going to be 100. Had it been 100%, whatever obtained 80%, that should have been 80% over there. It's carried over. But from this point onwards, say this is going to be W1 gram here, this is W2 gram here. Obviously, the yield is expected to be less than the theoretical weight. Am I clear to you? The theoretical weight. Let me take an example, specific example. Let me take a simple example. Not necessarily the, okay, we shall take chloroethane, converted into ethene. I have to take a 2-step, it's a single step process. If it is a single step process, if it is going to be 100% yield, assume it is 100% yield, whatever be the molecular weight of this, C2H5, Cl, carbon is 24, plus 5, 29, plus 35.5, that is equal to 0.5 here, 35, 40, 44, 64. Am I right? 64.5 grams of chloroethane. And this is going to be converted into C2H4. That is 24 plus 4. I should have got 28 grams. Am I right? Had it been 100% yield, if you take 64.65 grams, 64.5 grams of this 1 mole, and definitely I should have got, that is the maximum yield I should get, 28%. Why 100% yield? And if it is not going to be 100%, 80%, what is 80% of this? 28 into 80 by 100. 0.8, and that should be equal to 22.4%. Instead of 28 grams here, I am getting roughly 22.4. Am I right? 22.4. If I am going to get 22.8, I may not be able to calculate the percentage yield, or based on the percentage yield, I can calculate the percentage of weight of the product also. Again, this is going to be converted to the product. It is, had it been 100%, it should be the same percent, 100% yield, theoretical, but it is going to be 70%. So what should you calculate? This multiplied by 0.7, 0.7, because it is 70%. Supposing you have got one more step here, one more step here, and this is going to be converted to 40%, let's say 40%, 40%. The 40% of it is going to be converted to. So every stage it is going to be reduced. And if you are going to have more number of steps, greater the number of steps, lesser the number of percentage yield. So what is ideal? Single step process. And I remember there was one question here based on this multi-step process. Thanks for giving this question here. I have a method of preparation, both of them involve, let's say, it's an IIT question. A convert into B, B convert to C, two-step process. I got 80% here, and this is 30% here. Unfortunately, the second step is very, very poor. And they have given another method, method 1. Same starting material. The cost factor is also taken care of. And I am telling you the relevance to the industry. Now, this is going to be 30%. And this is going to be 80%. In this case, B is converted to C here. It's a very costly material. And industrial is not interested in wasting that even 1 gram to go down the drain. The question was, which of the two methods is ideal at the industrial level to prepare C? Both of them is good because both of them ultimately gives the same percentage yield. Number of moles, weight of this product into 0.8, isn't it? 80 by 100. Weight of this product, then from this weight of the product into 30 by 100. Here is going to be weight of this into, assuming that more or less the same weight, let's say. The question is, I can propose both the methods, or I can propose only the first method is ideal, or only the second method is ideal. Both the methods are not good. The answer is first method. Why do you propose? The answer is right. You are right. Why do you want to throw away the second method?
Because you get 80% after 30%.
After 30%. Because the so-called very important compound bought there with huge price, 70% of it itself goes down the drain. Only 30% of it is available. What does it matter whether 30% is going to be again converted to 30%? Overall yield is going to be 30%, assuming it is going to be 100%. So I want the starting material that is going to be very important for an industrialist. He wants that to be maximum amount converted into intermediate. He is not worried about the rest of the thing. Okay? Because reagents used in the second method, third method are very simple. Very simple. Okay? That's the reason why we have to make use of a step which gives you single step process, which gives you maximum yield. Excellent. Excellent. Now, the kinetics I told you, we have base, this is an experimental parameter. From that only I have to write the mechanism. Based on the mechanism only I have to come to this, not the other way about. Not the other way about. Because I have no idea what type of mechanism. Only when I am very certain about the mechanism, I can give you the molecularity. That was another question, which is to be determined first. Order of the reactions to be determined first, then molecularity, or both of them simultaneously determined, or molecularity first and the order of the reaction. Is that clear to you? That's a logical point in this. And what is going to be the third feature here? Have I started mentioning that? Third feature? No. Third feature, nature of the reactivity. I have already mentioned that reactivity of, what was the heading there? The nature of the halogen X. Nature of X. I have mentioned it. Okay, this is taken care of. Can this be taken as an evidence for the mechanism I have proposed? Yes. How? In one case, I take iodoethane, alcoholic AOH. I get ethene, plus potassium iodide plus water. In another case, I take chloroethane. Generally, fluorides are not used. I told you fluorides are useless compounds. Preparation itself is tougher job, highly explosive. Okay, even though you have taken so much of precautions, finally you find the yield is going to be much less. So whenever I say alkyl halides, I choose only alkyl chloride, alkyl bromide, and alkyl iodide. This was a question earlier. But in an industry, though alkyl chloride is going to be less reactive, generally alkyl chlorides are used as a starting material. The cost factor is much cheaper when compared to bromoethane, bromoalkane, and iodoalkane. I don't want to start a very high, very costly material and prepare this, because when it is being sold in the market, it is going to be much higher. Profit is going to be reduced. So generally that's the reason. Though it is going to be much cheaper, less reactive, it is cheaper. I don't mind using it again and again, increase the percentage yield. That's the reason why generally alkyl chlorides are used at the industrial level rather than alkyl iodide. It was, in fact, it could be asked as an assertion and reasoning also. What's the reason? Because it's so cheap. The cost factor, the cost of chloroalkanes. Now let me use alcoholic KOH here. And what happens? CH2, double bond CH2, potassium chloride plus water. I take 1 mole. I take 1 mole. And what is the percentage yield? Though it is not going to be 100%, assuming it is going to be 100% yield, but definitely you require higher conditions. Because it has got higher activation energy when compared to the cleavage of carbon iodine bond. We have already seen. So what is the reactivity? I will convert this into a question here. I have got K1 here, I have got K2 here. Which is greater? K1 is greater than K2, or K2 greater than K1, or K1 is equal to K2? K1 must be greater than K2. Why? Because this is faster. Why is it faster? It goes by the bond dissociation enthalpy. Is it happening in the laboratory? Yes, it happens in the laboratory. And is it also explained in the mechanism? Yes. Taken care of in the future? Yes. Therefore, it can be taken as an evidence for the mechanism that we have proposed. Is that clear to you? Next feature number 4. Feature number 4. Nature of alkyl halides. What is this nature of halide? X here, and what is the nature of alkyl halide? What are you going to mention here? Whether it happens to be a primary halide or secondary halide or tertiary halide. Would you expect a difference, a reaction, difference in the rate of the reaction here? Let us visualize. I don't need this. If I want to classify this as a primary, secondary, and tertiary halide, I need to have 2 hydrogen atoms for the primary. I need to have only 1 hydrogen atom and 1 alkyl group for this to be secondary. There is no alpha hydrogen atom. This is tertiary. I have already proposed a mechanism. What is the mechanism? What is the mechanism we are going to propose? Tell me. As usual, the OH minus ion will abstract the proton, beta proton. That is instrumental in forming a double bond. And finally, the halogen is removed. And we have taken, for the sake of comparison, same halogen. Identical conditions. You can compare the rate of the reaction only under identical conditions. What do you mean by identical conditions? The molar concentration should be the same. Reagent should be the same. Solvent should be the same. Temperature should be the same. Because as the temperature increases, the rate increases generally. You cannot do a reaction at one temperature and another one at higher temperature. There is no way of comparison. Generally, as the temperature is increased, the rate increases. So, all these parameters, experiment parameters are taken care of. Make a note of all these points that I was explaining to you. Same X, number 1. Number 2, same solvent. Okay. Concentration, same concentration, same temperature. The volume of the flask is also important under some conditions. Anyhow, that is negligible. Now, what is the difference here? It's a primary, secondary, or tertiary. Now, we have written the mechanism. Would you expect any change in the rate of the reaction here, or it's going to be the same? I have 3 options here. It is equal to K1, K2, and K3. K1 greater than K2 greater than K3, or K3 greater than K2 greater than K1, or any other permutation combination as per your wish, or none of the above, or all of the above. Yes, you feel K1 greater than K2, this is going to react fastest, most readily. Have you visualized the mechanism? You have to take into consideration the mechanism. It should be there before you. The reaction should be going. Okay? And then you should be able to. Yes? Oh, you always give the other way about. K3 greater than K2 greater than K1. This is the fastest here. This is the fastest here. Is that so? How many of you propose tertiary alkyl halides react most readily? Raise your hand. 1, 2, 3, 4, 5, 6. How many of you propose primary halides react faster? 1, 2, 3 only. So it goes by the majority. The reactivity is tertiary greater than reactivity. What is the conclusion now? Reactivity is tertiary greater than secondary greater than primary. Wonderful. Explanation. Now comes the IIT question now. Assertion and reasoning. Now that I have given you the answer, start thinking in that particular term. You have to find out why it should be so, why this is the most reactive compound. Wonderful, wonderful, wonderful. If you are going to put a double bond here, it is more substituted alkene. What is the general concept we have learnt earlier? More substituted alkene is more stable. More substituted alkenes are more stable. The concept is more, 1 minute, more substituted alkene is more stable. And because it is a more stable alkene, I will explain. I will take each one of the examples. It's more readily formed. It's more readily formed. The activation energy depends on the stability of the product, isn't it? If the product is more stable, activation energy is less. If the activation energy is less, it's a faster reaction. Faster reaction. Yes, what is that you wanted to?
Carbon and X bond is stronger in velocity.
Carbon atom?
And X.
X.
The bond between the carbon and X.
We have taken the same halogen here. Bromine, bromine, and bromine. Chlorine, chlorine, chlorine. The only difference is in the place of the 2 hydrogen atom, I got 1 alkyl group, I got 2 alkyl group. I shall explain to you. I shall explain to you. I shall explain to you. Though it is going to be, your term explanation is good. Visualization is perfect. Because the electron releasing group, he says, I got a methyl group. Probably that could be the answer, explanation. Why you wanted to propose this order. Methyl group, you have to say yes now. Methyl group. Methyl group releases electron. The carbon halogen bond is made stronger when you got 1 alkyl group, when I got 2 alkyl group. But in spite of it, the reaction goes the other way about. That is an IIT question now. How is it explained in terms of it? Okay. Now, we say, first of all, let me take CH, H, and chlorine. The product is going to be CH2, double bond, CH2, plus Cl minus plus H2O. It's a primary halide. Let me take secondary halide. No change with regard to the beta carbon atom. I got one methyl group or any alkyl group. One methyl group. What should be the product now? Encircle it. It becomes easy. Encircle it. Encircle it. I am always encircling in the opposite direction, anti. And that, in fact, it is going to be one of the features. I shall come back to that towards the end. Why not these two hydrogen atoms? Why not the hydrogen atom the same side? Why always the hydrogen atom away 180 degrees apart? Conformation, anti-conformation. I'll come back to that. Encircle it for the time being. I am removing these two. What should be the product? CH2, double bond. Are we not getting propene now? Yes, propene. Yes. This is secondary halide. Okay. Shall we take a tertiary halide now? Shall we take tertiary halide? CH3, H. We have one CH3. Both the alpha hydrogen atoms are replaced. Both the alpha hydrogen atoms are replaced. It becomes a tertiary halide. And this was a secondary halide. This is the primary halide here. This is the secondary halide. This is the tertiary halide. Now remove the hydrogen atom and the chlorine atom. You mark this as E2. Mark this as E2 because we want the mechanism also to be identical, not only the concentration, not only the halogen, not only the temperature, the mechanism also is identical. Can you compare the rate of one E2 reaction with the E1 reaction? Definitely not. It's a different pathway, it's a different pathway. Reactions undergoing the same mechanism, you can compare the rate of the reaction. Therefore, it should also be marked here, single step process. And what should be the product now? CH2, double bond C, CH3 and CH3. 2-methyl propene, isobutene. Make a note of it. 2-methyl propene, isobutene at every point. 2-methyl propene, isobutene. Now, in spite of the fact as suggested by him, the carbon chlorine bond becomes stronger and stronger here because of the electron releasing group. Methyl group releases an electron. Not only it strengthens the carbon chlorine bond, it strengthens the carbon hydrogen bond also. Of course, that is immaterial. There are two groups here. The carbon chlorine bond should have been the strongest here, but in spite of it, the reaction goes this way. Why? Stability of the product. The reaction, the rate of the reaction is decided by the stability of the product. More alkylated alkene is more stable. Remember, I think we made a statement earlier. What is the statement here? Which is the least alkylated alkene? Ethene. Or non-alkylated alkene. I am writing the order of stability. That could be another question for both the NCERT level and main examination. Given the different alkenes, you will be asked to arrange them, the increasing order of stability. I am writing increasing order of stability. It is less stable than monoalkylated alkene. One of the hydrogen atoms replaced by CH. Less stable, monoalkylated alkene. The next one, dialkylated alkene. Which is less stable than one more dialkylated alkene. One more dialkylated alkene. But it is attached to the same carbon atom, attached to a different carbon atom. Therefore, gem dialkylated alkene, attached to the same carbon atom. Big dialkylated alkene. And can't you again classify this into two? How? Cis and the trans. Cis and the trans. And cis is more stable, less stable than the trans. You have to say cis less than the trans. We have explanation for this also. This is going to be cis, more stable, less stable than the trans. The next one, or trialkylated alkene, CHR, trialkylated. And finally, tetraalkylated alkene, tetraalkylated alkene. Now, for us to understand how these alkyl groups increase the stability between an ethene, let's say between an ethene and propene, as per our explanation, ethene is less stable than propene. Because have we not explained the hyperconjugation in the case of propene? Is it conjugated? Is it conjugated propene? Yes. What is conjugated? What is conjugated? You tell me. What is conjugated? Single bond, double bond. Which single bond? The double bond and what are conjugated? Sigma bond attached to the alpha hydrogen atom. Sigma bond. The sigma bond and the double bond. Which sigma bond? Sigma bond attached to the alpha hydrogen atom. They are conjugated, separated by means of a single bond. Wherever there is a conjugation, there is a resonance here. And we write the no bond resonance here. We write the no bond resonance. This bond comes here and this goes. So what should be the next structure here? You don't put a bond there. You don't put a bond, because that particular bond is now present as a pi bond now. That particular bond is present as pi bond now. And we have a minus here. Now you see here, it's neutral. We have got one positive charge, one negative charge. Of course, the contribution is going to be maximum. The contribution is less. Most of the time it is going to remain in this format, right? And can I not use this hydrogen atom also, beta hydrogen atom? Can I not use this hydrogen atom? How many beta hydrogen, how many alpha hydrogen atoms, sorry. Here in this case alpha hydrogen. Because this is an alpha carbon. What is an alpha carbon? Carbon connected to, generally which is called an alpha carbon? Carbon connected to the functional group. What is the functional group here? Carbon-carbon, double bond is the functional group. Encircle that. The carbon connected to the functional group, carbon-carbon, double bond is the alpha carbon atom. And hydrogen attached to the alpha carbon atom are all called alpha hydrogen. Greater the number of alpha hydrogen atom, greater the number of resonating structures. How many resonating structures you could think of? One original structure, neutral structure, and plus 3, 4. I can write 2 more. So 1 plus 3, 4. And how many resonating structure? No conjugation here. Between, you tell me, between propene and butanene, which is more stable? That could be another question generated. CH2. What is butanene? You encircle the alpha hydrogen atom. 1 plus 3, 4 resonating structures. 1 plus 2, 3 resonating structures. Therefore, propene is more stable. This was asked once. IIT question. Can you suggest one alkene? I think we have discussed it earlier. One alkene which is the most stable alkene based on the hyperconjugation only. Or I will give you, I will convert this in another question. Hydrocarbon. A hydrocarbon, I don't know the molecular formula. I don't mind giving you the 1, 2, 3, 6, C6H12. The hydrocarbon is C6H12. Hydrocarbon is C6H12. This hydrocarbon alkene has got 1 plus 12, 13 resonating structures as per the hyperconjugation. No bond resonance. Therefore, the structure is, the compound is. So, what should you do? How do you do? Now, in this case, I can convert this into the same question for this molecule. How many resonating structures? I got 4 resonating structures, original structure. So, 4 minus 1 original structure. The 3 are through the hyperconjugation. Whenever you have got 3 hyperconjugated structure, there should be 3 alpha hydrogen atoms. All the 3 alpha hydrogen atoms are present in one methyl. Therefore, it's a methyl ethene. Methyl ethene is propene. Now, here I told you this particular compound has got 13 resonating structure, hyperconjugated structure. Therefore, minus 1, the original neutral structure, there should have been 12 alpha hydrogen atoms. The 12 alpha hydrogen atoms should be present as 4 methyl groups. So, you put a double bond, carbon carbon double bond, and put 4 methyl groups. This is the only way of assigning the methyl group. And this was one of the IIT questions earlier. Tetramethyl for this question.
Yes, sir. It's there, sir. R2, CW1, CR.
Yeah. I have taken R as the methyl group. But if R happens to be ethyl, I'll ask you. Tetraethyl ethene and tetramethyl ethene, which is more stable as per the hyperconjugation? Tetramethyl, because methyl group has got 3 alpha hydrogen atoms. Ethyl group has got how many alpha hydrogen atoms? Only 2. How many hyperconjugated structures for tetraethyl alkene? 2 plus 2 plus 2 plus 2, 8, 1 plus 8, there are only 9 resonating structures. Isn't it? Isn't it obvious now? More alkylated alkene is more stable. Now, you look at this. We have written the molecule, we still have that product here, ethene, primary halide. This is obtained from the secondary halide. This is obtained from the tertiary halide. How many resonating structures? Only 1. No hyperconjugation here. How many resonating structures? 1 plus 3. 1 plus 3. 4 resonating structures. How many resonating structures? 1 plus 3 plus 3. 7 resonating structures. And as and when you put the alkyl group, especially the methyl group, now you see here, which particular reaction is going to be faster? You have a methyl on the alpha carbon atom or other alkyl groups on the alpha carbon atom. Tell me. Methyl group. Presence of a methyl group and the alpha, that's a feature? No. A presence of methyl group and the alpha carbon atom will increase the rate of the reaction because it increases the stability. Is that clear to you? Now, it is not the bond dissociation enthalpy. We are supplying sufficient energy for the molecule to break, and depending on the stability of the product. Stability of the product. Because delta H, this is very important for me. So, that is going to be the next feature. What was the first feature? What was the first feature? Let us recall without looking at the notebook. Don't go back to the notebook. It's a single step process, high percentage yield. The second step is the kinetics. The reaction goes by second order kinetics. And based on that, we have proved that molecularity is also 2. And order is the experimental parameter and molecularity is the theoretical concept. Okay? The third one is the nature of the X. Good living group. Among the halogens, Ri reacts faster than RBr, reacts faster than RCl, RF. RF. Again. RF. The third factor is alkyl halide. Alkyl halide or nature of the alkyl halide, tertiary greater than secondary greater than primary. Now, in fact, I can give a different explanation now. That is for the advanced question. Why tertiary halides are more reactive than secondary halides, more reactive. I am going to introduce one more concept now. Quickly draw the reaction. I got H here and OH minus ion in alcoholic medium. I am leaving some space for me to draw the transition state of a through. Structure of the starting point, structure of the product, structure of the starting point here. I am supposed to write a structure that is coming over here with a maximum potential energy. In fact, that is called transition state. What is a transition state? It's a structure of the reactants and the substrate, reagent and the substrate both put together at the transition state. What is the transition state? When it has got the maximum potential energy. Okay? It is the potential energy of both the substrate and the reagent It's the status of reagent and the substrate, or the structure of the reagent and the substrate which has the maximum potential energy. This is called the transition state here. It should keep. Now we shall visualize it. What is going to happen here? When it is going to be point A here, when it is going to be point B here, at point C here, and this could be another IIT question, advanced IIT question. At point E here, and point phi almost towards the product here, and point G product. We shall come back to this. Different points. One at the starting point, slightly higher. It has started climbing the hill. It has started climbing the hill. It is almost towards the transition state, top of the hill, but not reached the top of it. This is going to be the maximum, topmost point, activated complex. What is the other name for this? Activated complex. Started sliding on the other side of the hill, E, and far away from that, towards the product, and this is the product here. What should happen? Now, I will put the carbon hydrogen bond dotted line. Wherever the bond is broken, wherever the bond is made, I represent it by dotted line. Bond making and bond breaking. This is a bond breaking process. And what is the bond making process? I got OH here, dotted line, dotted line. Is there any disturbance in the sigma bond? No. But sigma bond becomes shorter, that's all. Okay? And I am going to put a dotted line here indicating that a lateral overlap also is taking place. Lateral overlap is also taking place. And what should happen to these bonds? I am not worried. And this also becomes longer now, X here. That's all. You put them in bracket here, and that should be the structure of the transition state. And this is converted to the final. Let's say the whole process is over. Where are we now? Terminus. We have reached the terminus, G. And what should be? These three, water, H2O. Okay? H2O, non-linear molecule. And what should happen to the alkane here? We have got double bond. And what happens here? Plus X minus. Okay? Now, most of the questions related to the mechanism in IIT can be answered by knowing the structure of the transition state. More than the structure of the starting compound, more than the structure of the product, structure of the transition state is very important. Even questions like assertion and reasoning, multiple answer, multiple choice, most of them can be explained based on this transition state. Now, yes, this is explained based on Hammond's postulate. Hammond's postulate. Hammond's postulate. Hammond's postulate. Now, what does that Hammond's postulate tell you? It is meant for an endothermic reaction, condition 1, endothermic process. And elimination is an endothermic process because only on heating the reaction takes place. Of course, we can also extend it to exothermic reaction. It's not going to be that useful. Yes. Now, let me draw one more diagram. Then we'll come back to this. Endothermic process. I have a reactant here. Of course, I have drawn the, just for the sake of example, exothermic reaction, but it should be endothermic process. The same points here. Anyhow, I'll come back to that. We have the product here, alkene. It goes over there, slides over here. Now, assume that the reaction is reversible. This is the activation energy for the forward reaction. For the reverse reaction, for the product converted into reactant, for the reverse reaction, which is the reactant here? The product is the reactant. And what is the activation energy? This is the activation energy. In endotherm, and this could be one simple question for the main examination. Which of the following statements right? For the endothermic reaction, the activation energy for the forward reaction is greater than that of the backward reaction. Yes, true. Or it could be other way about. For endothermic process, activation energy for the reverse reaction greater than that. They are identical. None of the above. Similarly, for the exothermic reaction, activation energy, the forward reaction should be less than that of your backward reaction. Are you able to visualize? Immediately bring in the potential energy diagram in front of you. Exothermic reaction. Now, since this is an ideal situation, but that does not happen. Both the reactant and the product having the same activation energy. Why? Because the structure itself is different. Even for the conversion of allotropes, same element, diamond to graphite, alpha sulfur to beta sulfur, and beta to alpha. Okay? They are different format. They are different physical forms. So they cannot have the same potential energy. Would you expect them to have the same? Therefore, there should be a variation in the potential energy between the reactant and the product. Whenever there is a variation in the potential energy between the reactant and the product, obviously the activation energy for the both forward and backward should be different. Why should it be different? Assertion and reasoning. Because the reactant is different from the product. Even though for the isomers, let it be isomer. Have we not seen isomerization reaction earlier? N-butane to isobutane. Shall we recall? N-butane to isobutane. In which case, the energy of activation is going to be less. Conversion of N-butane to isobutane or isobutane to N-butane. Another question. N-butane to isobutane. Isobutane is more stable. Isobutane is more stable. That delta G has got greater negative value. Isobutane. Isn't it? So, definitely one reaction, the activation energy is going to be less. Okay, that apart. So, that could be another question. You keep consolidating all the questions. Every statement can be asked in the form of a question. And this is going to be. Now, therefore, since they are not identical, structures also are not going to be identical. Structures also will not be identical. Structure is different. Based on the structure only, the potential energy of the molecule, the hidden energy of the molecule. Isn't it? Now, tell me, I will ask you another question without explaining the Hammond's postulate here. I am comparing the structure of the transaction state, activated complex, is much closer to the structure of the product or much closer to the structure of the reactant? Product is closer to the activation energy. This is far away. In an endothermic reaction, what is the concept, underlying concept here? The structure of the activated complex is much closer to product. So, in an exothermic reaction, it should be other way about. Now, let me take this exothermic reaction. This is the activated complex. Isn't it much closer to the reactant here? So, if you want to, what are you doing in the case of elimination reaction? Based on the stability of the product. Stability of the product. The product which is more stable, more alkylated alkene is more stable. Accordingly, we write the rate of the reaction. Is that clear to you? Therefore, I am giving you the statement now, Hammond's postulate. The factors affecting, first listen. Factors explaining the stability of the product also explain the stability of the transition state. Also explain the stability of the transition state. What do you want to infer from the stability of the transition state. You tell me, I got two different transition state. One is most stable transition state, the other one is most difficult transition state. In which case activation energy is going to be less? Let's say this is going to be an endothermic process. Another reaction, this is going to be an endothermic reaction. Transition state 1 here and transition state 2 here. This is more stable. Since it is more stable, more readily formed. And would you expect that reaction to be faster or slower? Faster. Now you see here, that is making use of it. It is not because of the product is going to be more stable. So write the Hammond's postulate now. Factors explaining the stability of the product. Factors explaining the stability of the product. Factors explaining the stability of the product also explains the stability of the transition state. Also explains the stability of the transition state. Stability of the transition state. Also explains the stability of the transition state. And that is what we are going to do. Now look at this. We will come back to this diagram A, B, C, D, E, F, G. We will take up this. In the first case, I will put the first circle. It means they are the starting compound number 1, primary halide. The second circle, it indicates it's a secondary halide. And third circle indicates, instead of drawing 3 different structures, I have drawn it. I suppose it is not confusing to you. You can draw it differently also. Putting H and H here, another case R and H here, third case R and R here, tertiary. Therefore, that particular, now you visualize a transition state wherein you have got R and R. That transition state is more stable. Why should it be more stable? Because it is similar to that of the product. What did you explain in the case of the product? More alkylated alkene is more stable. Therefore, the transition state leading to the formation of more alkylated alkene is also a more stable transition state. Transition state leading to the formation of more alkylated alkene, a transition state leading to the formation of more alkylated alkene is a more stable transition state. So I got a transition state 1 here, I got a transition state 2 here, I got a transition state 3 here, TS1 and TS2 and TS3. I can ask you lots of innumerable number of questions. What do they suggest? Represent, reflect. It's a transition state of the tertiary halide. Transition state of the secondary halide. You put tertiary halide, secondary halide, a primary halide. Why is it so less stable? Because the product, accordingly, you have to, there should be a variation in the product also. Now, how should it behave like this? This is the whole overall reaction is endothermic, and this comes here, and this comes here. You see here, what is going to be delta H here? Delta H is going to be this for the tertiary halide. What should be the delta H here? That should be the delta H for the secondary halide, and that should be the delta H here. And delta H also explains the stability. Have we not studied about the enthalpy of hydrogenation related to the stability here? And why is it more stable? Because why is it potential energy less? Because it's more stable. And corresponding activation energy, corresponding transition state. And that is Hammond's postulate. Factors affecting the stability of the product also affects the transition state. Factors leading to the formation of a more stable product also forms a more stable transition state. Yes?
Doesn't the stability of the product and the reactivity also depend on the beta carbon because in the alkyl groups
Definitely the beta carbon, not only the beta carbon atom, beta hydrogen atom, the other substituents also will affect here. That's going to be too complicated for us. We are taking step by step. We have simply forgotten about. we just simply forget about the alpha carbon atom, substituents alpha carbon atom. It is only the beta carbon atom. Then we will come back here. We have already taken care of this. We will come back here. What happened if we have got hydrogen and hydrogen here? What about if we have methyl group here? We will come back here. And that also should definitely vary your transition state. But as I told you, we are taking care of the product. The product means a carbon-carbon double bond, depending on the number of, obviously, if you have got a methyl and methyl tetramethyl, and you have got an alkyl here, we have got an alkyl here, we have got an alkyl here, and that transition state is going to be most stable transition state, because that is a tetraalkylated alkene. Yes? Not only depends on the substituent and the alpha carbon atom, it also depends on the substituent and the beta carbon atom. Which is my statement right? Which of my statements right? Tell me. Having more substituents on the alpha carbon atom and the beta carbon atom gives you a more stable product. Having more substituents on alpha carbon atom, less number of substituent beta carbon atom, or more number of substituents here, less number of substituents, or no substituents here. I have framed a beautiful multiple choice question. So you should have alkyl group here, alkyl group here, alkyl group here, alkyl group here, and that is the tetraalkylated alkene. So the stability of the product not only depends on the substituent and the alpha carbon atom, it also depends on the substituent and the beta carbon atom. The same feature, make a note of it, I will come back. Same point here. What did I explain here? The same point? Nature of alkyl halides. We are still in the fourth point. Isn't it the fourth point? Yes. Nature of the alkyl halide. Nature of the substrate, nature of the number of alkyl groups at both the alpha and beta carbon atoms. Number of alkyl groups at both the alpha and the beta carbon atoms should alter the stability. And what does it explain? Go back to the point number 1. What we made, stability of an alkene. More alkylated alkene is a more stable alkene, isn't it? Yes. Is there anything else you wanted to ask?
Sir, so there's an example, sir, in which you can have two substituents, two methyl groups attached to the beta carbon.
Yes, two substituents, the beta carbon atom.
And you have a CH2X.
CH2, X here, yeah.
And then another compound, you have a CH3 and
Only one here and one here.
CH3 attached to a secondary alkyl halide.
Okay, here, CH3.
CH3 there, and here are the no methyl groups.
Only one.
No.
Okay. Yes. Now, ultimately, depends on the position of the alkyl groups. Now tell me, what should be the product? It is all decided by the product here, product stability. Yes. Now you see here, are you not going to end up with the dialkylated alkene? And this is going to be, encircle the hydrogen. What should be the product here? CH2, double bond C, CH3, and CH3 here. What does that matter?
If you don't have the one, if you have only one CH3 in the alpha carbon.
Okay, naturally. Finally, number of alkyl groups only. It goes by the number of alkyl group present on the number of alkyl groups attached to the alpha carbon atom and the beta carbon atom. Yes, definitely. Greater the number of, generally, let us not go into deep, in the sense have a methyl group and alpha, beta, ethyl here. I got methyl here, ethyl here. Definitely there could be a smaller variation here. The overall variation depends on the number of alkyl groups attached to alpha carbon atom and the beta carbon atom. Okay? And as you increase the number of alkyl groups and the alpha and beta, the stability should increase. Keep writing. Is that clear to you? Now we will come back to that particular point. We are still in the point number 4, feature number 4. What is that feature number 4? Should not forget about that. Nature of alkyl halides. Feature of 4, nature of this. Now let me draw the same points here. using an endothermic process. I gave you an exothermic process. This is an endothermic reaction, and this is what is happening actually in the alkene. And I say this is point A here, much closer to that point B, much closer towards the transition state point C, point D. Please write it once again. This is going to be point E, and this is point F, and this is point G. Point G. Now, the transition state I wrote it, but that was incomplete. The transition state I wrote it, but that was incomplete. No one noticed it. Shall I, once again, I need to have a starting compound for me to write the transition state plus OH minus ion. What should be the transition state here I wrote? HO, okay, dotted line H here, and this in turn is connected to a dotted line, a carbon, H here, a sigma bond, a pi bond in the form of a dotted line, and a dotted line towards the chlorine here. Transition state. I don't want the product. We have seen the variations, isn't it? Have you not seen the? This comes closer and closer. Supposing, assuming it is good, bond angle is going to be 90. Bond angle between the hydrogen atom and the oxygen atom 90 to start with, or it could be any bond angle, depends on the orientation, isn't it? Would it always be 90 here? No. It can be 180 also. The OH group is coming and attacking here, directly opposite, anti. So could you fix the bond angle between the initial stage? No. But definitely I can fix the bond angle when it is converted to the product. Water, what is the bond angle of water? 104.8. It comes to that level. So that shows the end of the reaction, Water is formed. At that stage, the bond angle becomes 120. I can ask you the question, same question. When the bond angle becomes, this hydrogen and this hydrogen atom becomes equal to 104.8, 105 roughly. And what the bond angle between the two hydrogen atoms? 120. The concept is asked in the form of a question. That is how the IIT questions are framed. So, my dear students, please try to understand the concept. If there is a concept clarity, definitely you should be able to answer any type of question. Yes? I can ask you the bond distance also. Okay, don't bother about all. This is the product here. I told you the structure of the transition state is incomplete. Now, for us to answer this question, I also need the structure of the product. Plus H2O plus X minus. And I have taken this as an X here. Let me also treat this as an X here and X minus. X minus. Something is missing in the transition state. The mechanism is not complete. Okay, let us not waste time. Or you want to keep thinking? Tell me. Yeah. You can also sip water if activate yourself. No. Even if I give you a whole day, it's hidden. I'll tell you. What is the charge of this? Charge is missing. Charge is missing. What is the charge of ethene? 0. What is the charge of OH minus ion? -1. What is the total charge of both the reagent and the substrate? -1. 0. 0. Charge is taken care of. The charge is not taken care of here. Can this be neutral here? No, definitely not. Why should it not be 0 here? Because you look at the charge, the starting point. This is the point A. point A. What is the charge on the oxygen atom here? Minus 1.0. Isn't it? It is going to be minus 1.0. And what is the charge here? The neutral. 0. So what happens to the charge of the oxygen atom? Keeps decreasing. Therefore, it should be a decreased charge on the oxygen atom. That we represented by delta minus here. Diminished charge. Similarly, what is the charge of the halogen atom here? The starting point, 0. What is the charge of the product? Minus. So charge is being initiated in the halogen atom, and it cannot be 0 here. Therefore, starts acquiring the electrons, delta minus here. Delta minus here. Okay. What should be the total charge? I'll ask you one question based on this. You tell me. What should be the total charge of the, on the halogen X and oxygen here? Minus 1. Minus 1.0. Both sum of these two charges. 0.7, minus 0.7, minus 0.3, minus 0.6, minus 0.4, minus 0.5, minus 0.5, roughly. And equal charges, probably it should be at the transition state. Now, shall we visualize? And that is what I have asked you. What should be the A represent the charge on the oxygen atom, the charge on the halogen atom, point A, point B, point C, point D, point E, F, and point G. What should be the charge on the oxygen atom at the point A? Minus 1, minus 1.0. This is going to be 0. What should be? I can give you the separate question. It should be much closer to point. It could be 0.9. It could be 0.9. I can give you 4 different answers. What the point, the charge on the oxygen atom at the point B, minus 0.9, minus 0.5, minus 0.4, or minus 0.1, or 0. What should be the answer? This is going to be 1.0 here. It should be much closer. Slowly, it has lost only a few electrons. It could be minus 0.9, 0.9 here. What is C here? It is, let's say, D is going to be point. Assume that this is going to be minus 0.5. It is much closer. I can say it is going to be minus 0.6 here. Isn't it? Minus 0.6 here. Now on the side, when it's going to slide on the other side, should it not decrease? This is going to be 0.5, and this point E, minus 0.4. This is going to be minus 0.1, and this is going to be 0. Instead of 0.9, they can give you minus 0.1, minus 0.4. And same way, in the case of the halogen atom, X here, it should be the other way about. If it is 0.9, it should be 0, minus 0.1. If this is going to be 0.1, minus 0.9. The charge on the X keeps on increasing. It could be, that could be yet another question in the main examination, because we are able to visualize the reaction. We are able to visualize the reaction. Okay. So that is the feature number 4, nature of the alkyl halides. And what is more important, the structure of the transition state. Structure of the transition state. In future, whenever you write the mechanism, please take note of the transition state. Most of the questions can be answered by looking at the structure of the transition state. Okay. Yes, feature number 5. Feature number 5. It has to be explained this way for us to understand and answer most of the questions. And we are able to bring the molecule in front of us, and we are able to visualize it also. Yes. Now, what is feature number 5? Stereochemistry of the reaction. Stereochemistry. And in this, we are going to stereochemistry of the transition state, structure the transition state, and once again structure the product. Okay. Now, E2 reaction goes with anti-requirement. This is going to be, it requires anti-periplanar conformation. Anti-periplanar conformation. I mentioned this in the beginning. Why did I want to choose the hydrogen away from the halogen? Anti-conformation. That is important for me. Anti-periplanar conformation. You know what is an anti-group? Dihedral angle 180. Staggered. What if you have dihedral angle 60? What is if you have 120? 120 is unstable, eclipse conformation. 0 degree dihedral angle, most unstable here. Let us take all the extreme cases. 0 dihedral angle and 120 dihedral angle, and we can easily visualize the Sahas notation. Let me draw the Sahas notation here. CH3 X here. The relative position of the halogen and the beta hydrogen. This is the beta hydrogen atom. What is this conformation? Anti-conformation. Though it is going to be here, the probability, you don't rule out that. A base can abstract this particular proton also, this particular proton also. It is identical when compared to this. What is the relative position of this hydrogen atom when compared to this? Tell me. When compared to the halogen, what is the relative position of this hydrogen atom? Gauge. Skew. Write it. Skew. And these two hydrogen atom anti-hydrogen. Now, why do I need anti-hydrogen here? The OH minus ion will abstract this far away from the leaving group. There is no steric effect at all. Steric effect is completely removed. There is no steric factor here. With the result, the transition state becomes more stable. Whenever the transition state becomes more stable, it's a faster reaction. You have to write down these points. Transition state is faster. Now, let me draw leaving group here and hydrogen here. Gauge conformation or skew conformation. Regarding this, anti-conformation. Now, isn't it enough to just tell anti-conformation? Why anti-periplanar conformation? When do you need planarity? When do you use the term planarity? To explain what? To account for the resonance. Resonance. Isn't it? I remember to have heard this particular statement earlier. Resonance. Important condition for the resonance is planarity. Important. That is why benzene is completely delocalized, because the entire molecule is planar. Whenever there is a disturbance in the with regard to the planarity, resonance also will be disturbed. Planarity is important. Why do you need, when are you using resonance here? Tell me. Only then I need to use periplanar conformation. Stability of alkenes, hyperconjugation. Hyperconjugation is also a kind of resonance. No bond resonance. No bond resonance. So planar, unless it is planar, resonance cannot be induced, isn't it? Therefore, now you understand. Now look at the transition state. This is going to form a transition state. Let us take one by one. Have you taken down, drawn these two things side by side? So this is going to form a transition state. This is going to form a transition state. Transition state 1 and transition state 2 here. we are not allowing the carbon atom to rotate. It's always anti, that's all, freezed, frozen. This is also hydrogen, are not allowed to rotate. It's always Q, but still staggered. But the transition, which transition state is going to be most stable? Because there is a perfect planarity. The planarity in the OH minus ion now comes here and attacks this hydrogen atom, and this is responsible, isn't it? This goes over there, and finally X is removed, X minus. Now, because of the close proximity, it is not allowed to come closer. It is disturbed. It finds it difficult to abstract a gauge proton, skew proton. At the same time, the OH minus ion is able to abstract the antiproton, and that leads to the planarity. Therefore, that particular conformation is called anti-periplanar conformation. My dear students, I have already told you the stereochemistry is very important. There are two types of reactions I told you, stereospecific reaction and stereoselective reaction. One particular isomer gives you exclusively that particular isomer only, meso compound only, 100% meso. Another reaction gives you 100% DL. I will give you the example later. Let me not take up that now. Stereochemistry of E2 reaction is a separate chapter by itself. I am just giving you the inputs right now for that. Yes. Now, therefore, when it is not allowed to rotate, but that is not happening in nature, in practice, it keeps rotating. When it is about to attack here, what is the position? Gauge. That's all. Okay. When it is going to about to attack here, it's anti here. And what about when it is going to be full? Let me take this conformation. What is this conformation? Let me take Y here, Y here. Putting 2Y here is the eclipse conformation. X here, hydrogen here. What is the dihedral angle here? Dihedral angle is fully eclipsed. Isn't it fully eclipsed here? You have to bring in all these parameters, whatever you have studied in the 11th standard. All these parameters, conformation. If you do not have any idea about the conformation, you may not understand head or tail of what we are doing right now. That is why I have been telling you repeatedly, your 11th standard portions are very, very, very important. Keep revising every day. Even when you go to the 12th standard, keep revising the 11th standard portions. Keep looking at the videos of the 11th standard portions. That should definitely give you greater clarity. Easy to crack the examination. That is the secret behind the scoring very good marks in IIT. Full eclipse here, and OH minus ion. Where is that OH minus ion? Let's say the OH minus ion is in between. The OH minus ion is in between here. If it is going to be here, it is not going to. Naturally, the OH minus ion also should take its proper position, orientation. The hydrogen is here. What's the point in OH minus ion searching for the hydrogen somewhere there? So it has to transition energy, translation energy. I told you translation energy is an important factor in intermolecular reaction. Don't you remember the difference between intramolecular reaction and intermolecular reaction? This is an intermolecular. The OH minus ion, if it's there, energy must be supplied. It has to come back here. It is not enough. It cannot attack 90 degrees. It has to attack 180. All these parameters are important. And you have got hydrogen here, and you have got another halogen here. So it is going to be completely eclipsed here. Maximum steric hindrance. Maximum steric hindrance. Now I can generate one question based on the main examination. What should be the dihedral angle? What should be the dihedral angle? Increasing order of reactivity. Write it. Increasing order of reactivity when the dihedral angle between X and beta hydrogen atom is dash. Tell me. Now the answer is very simple. Increasing order of reactivity. Which is the least reactive conformation? Fully eclipsed, 0 dihedral angle. The next one should be? Can I say 0 less than 60, less than 120, less than 180? Or 0 less than 120, less than 60, less than 120 is also eclipsed. 120 is also eclipse. What is 120? And the halogens here and the hydrogen atoms here. The dihedral angle between these two, the halogen and hydrogen, probably you can make a note of it. You can make a note of it. Look at this. I have eclipse. For eclipse, you have to draw eclipse here. 2y. And y and inverted y, staggered conformation. And where do you have this halogen here? Where do you have the hydrogen? Beta hydrogen. This is the beta hydrogen atom. What is the dihedral angle? Dihedral angle is 120. Partially eclipse conformation. And eclipse conformation again is going to offer the steric factor, isn't it? So increasing order of reactivity, tell me, in terms of dihedral angle, 0, less than 120, less than 60, less than 180. Increasing order of reactivity in terms of dihedral angle. In terms of dihedral angle. Anti-periplanar conformation. You get the required conformation only when the dihedral angle is 180. That is why it is called anti. That conformation is called anti-conformation. That is the required conformation. What is the stereochemistry? Required conformation for the E2 reaction. Not E1, not E1CB, E2 reaction. Required conformation for the E2 reaction to take place is anti-periplanar conformation. Why is it called anti-periplanar conformation? Because, tell me, the OH minus ion should attack which hydrogen atom? Which hydrogen atom? Obviously beta hydrogen atom. At what dihedral angle? 180. Why planarity? Because it leads to the resonance, stabilization of the resonance of the transition state. Not only the transition state, the products also. Anti-periplanar conformation. Another one. Structure of the product. E alkene more readily formed Z alkene. Ease of formation. Ease of formation. Ease of formation of an alkene. What is an E alkene? Trans alkene. What is Z alkene? Cis alkene. Remember? Refers to the priority. CH3. CH3. If the groups are the higher priority, if the groups are the higher priority, always encircle the groups are the higher priority. Encircle the groups are the higher priority. Based on the atomic number, if they are on the opposite side, it is E configuration. It is Z configuration. The priority, carbon gets a higher priority. Carbon gets a higher priority. If they are on the same side, it is going to be Z. Trans alkene is a Z alkene. Trans alkene is a Z alkene. Now, why should? Now, main exam, not even main examination question. NCERT question, which we have discussed this umpteen number of times with alcoholic KOH. This is the n+1 time we are discussing. The number of products. How many products are produced? Three. Okay? That's for the NCERT. And main examination, why don't you arrange them in increasing order of stability, percentage yield? Increasing, which is formed least percentage yield? Tell me. But-1-ene. Because this is a beta hydrogen, this is also a beta hydrogen atom. Though the statistical probability is more, that could be another assertion and reasoning. They can tell you 2-chlorobutane conversion of but-1-ene on treatment of the alcoholic KOH, first statement, it's a correct statement, but that's not one of the products. They can say it's a product here because the statistical number of beta hydrogen atom is more. The number of beta, that's a correct statement, but the previous statement is not the major product. What did I tell you? 2-chlorobutane on treatment with alcoholic KOH gives you but-1-ene as a major product. That is not the major product. And I am trying to explain my statement because there are more number of beta hydrogen atoms. We have already seen greater the number of beta hydrogen atom, faster the reaction, but that does not happen here. That's an exception here. 3 beta hydrogen, 2 beta hydrogen atom. What is the other product here? Cis-2-butene. Cis-2-butene. What is going to be the third product here? Trans-2-butene. These are the bond line formula of tris-2-butene and trans-2-butene. Now you know. And this is going to be less than, this is going to be less than. Increasing yield of, which is formed with the maximum yield. Tell me. Why? Tell me, correct statement based on whatever we have learned. Anti-conformation. You call this anti-conformation? Is there any conformation for the alkene? Conformation can be used only for the free rotation. Wherever you have free rotation, it has restricted rotation. Why? The yield is more. Assertion and reasoning. What I have told you is a correct statement and explanation for this. Tell me.
More hyperconnected structures and less steric hindrance and zero dipole moment.
Hammond's postulate once again. The transition state leading to the formation of trans-2-butene is a more stable transition state than this. When the transition state is more stable, the activation energy is the least. Therefore, percentage yield is going to be more. That is the logical statement you have to write. That is why we have to keep repeating the Hammond's postulate. I told you already, the structure of the transition state is more important for us to explain most of the questions. What is the explanation you are going to give? The transition state leading to the formation of trans-2-butene is a more stable transition state, or the most stable transition state. What should be the transition state leading to the formation of but-1-ene? Least stable transition state. Then I can generate one more question, isn't it? Can't you write the decreasing order of activation energy? What should be the activation energy for the combination? You tell me. What should be the activation energy? Which has got the maximum energy? Reaction 1, reaction 2, reaction 3. Which has got the maximum activation energy? 1 has got maximum activation energy. The next one is going to be the smallest hill. Smallest hill. And that is this structure of the product. Transalkene is always formed during the reaction. More alkylated alkene. These two are more alkylated alkene. This is the less alkylated alkene. More alkylated alkene. More alkylated alkene. And that is the transalkenes. What is that you have to write? Transalkenes formed faster than cisalkene. Okay. Now we have to learn a lot more things about E2 reaction. Maybe another 3 hours or 6 hours on E2 reaction alone. Anyhow, we will just stop this E2 reaction, then also know the E1 reaction. So easy for us to compare at this stage. Though E1 reaction also has to be dealt with in detail. So we will switch over from E2 reaction to E1 reaction. E1 reaction. Now, maybe I will give you one more feature, one more evidence for the E2 reaction. Hydrogen deuterium isotope effect. One more. What is the feature here? Feature number? 6. Feature number 6. Hydrogen deuterium isotope effect. CH3, CH2, Br. alcoholic KOH, K1, their product is CH2 double bond CH2 plus KBr plus H2. CD3 CH2 Br, alcoholic KOH. We will call that rate constant as K2. What should be the product? CD2 minus, CD2 double bond CH2 plus KBr plus, what should be the product now? What should be the product? I think that itself can be a separate question. The product form is equal to H2O, D2O, HOD. Yeah, OH from here and deuterium from here, or DOH. Isn't it? That should be. So the answer is this, HOD or DOH. Now, you know the answer. We have been discussing this earlier. K1 greater than K2, K1 is equal to K2, K1 less than K2. K1 greater than K2 reaction. Yes. K1 greater than K2 reaction. To what level? Is increased by how many times? K1 greater than K2 by how many times? It depends on whether it's a primary isotope effect, secondary isotope effect, or solvent isotope effect. I shall explain to you in detail about the three different types of isotope effect, but here whenever K1 by K2 is roughly 7, equal to 7, it is called primary isotope effect. This particular reaction 7 times faster than this particular reaction. The rate constant, don't you think the rate constant gives you an idea about the rate of the reaction? What is the underlying concept? You say relate the rate constant and the rate of the reaction. How do you relate the rate constant and the rate of the reaction? Higher the value of rate constant, faster the reaction. Faster the reaction. Therefore, this should be faster at least by 7 times, roughly. It could be 6.5, any value around 7. If the rate constant, the ratio between, to make it more clear, I will put that K1 as KH, I will put K2 as KD, because I am cleaving a carbon deuterium bond. Okay, instead of having abstract numbers K1 and K2, straight away KH, that tells you I can convert this into KH here and KD here, and I am cleaving a carbon hydrogen bond, I am cleaving a carbon deuterium bond. Definitely cleavage of carbon deuterium bond. You know, bond dissociation enthalpy is stronger, carbon deuterium bond. Why should it be stronger? Why should it be stronger? Why should it be stronger? Carbon deuterium bond is shorter than a carbon hydrogen bond. Shorter the bond, stronger the bond. Carbon tritium bond still more shorter. Now, whenever this value is equal to 1, what is the conclusion? No hydrogen deuterium isotope effect. It's not the first time we are seeing this hydrogen deuterium. Have we not seen it? Aromatic electrophilic substitution reactions. Halogenation, nitration, sulfonation, Friedel-Crafts alkylation reaction. Is a carbon halogen bond broken in the rate determining step there? Yes or no? Oh, we have to know the mechanism of aromatic electrophilic substitution reaction. Nitration of benzene. Visualize it. I am not going to write it. We have seen it. How is nitration done? First step, generation of nitronium ion. That is not the part of the reaction. The first step actually, attack of the electrophile on this to form a sigma complex. Are you able to visualize it? And that is the rate determining step. Then what happens subsequent to the rate determining step? Cleavage of carbon hydrogen bond. Now tell me, in aromatic electrophilic substitution reaction, does the carbon hydrogen bond, is it broken in the rate determining step or a fast step? Fast step. So, if the carbon hydrogen bond is not broken to the rate determining step, there cannot be hydrogen deuterium isotope effect. Therefore, aromatic electrophilic substitution reaction Kh by Kd must be equal to 1. It is immaterial whether you have hydrogen or deuterium. Is that okay? Okay. Now tell me, why is it so? Because I'll convert this into assertion and reasoning. Kh by Kd is equal to the order of 1, and there is going to be, this is called primary isotope effect. Primary isotope effect. It's very simple. If the carbon hydrogen bond is directly broken in the rate determining step, then there is a secondary isotope effect. Secondary hydrogen. Secondary isotope effect. What happened when this compound is reacted with, tell me, KOH? What should be the product? A bromine from here and hydrogen from here. The product should be, tell me, CH2 double bond CD2. Here also CH2 CD2. Same product but different starting material. What is the difference? What is the difference? Now in this case, what happens? This is going to be involving secondary isotope effect. Kh by Kd definitely is not equal to 1, but definitely is greater than 1.1. Greater than 1.1. Whenever it has got greater than 1.1, definitely it has got isotope effect, but up to 2.0. Not as good as the 7 here. If it is 7 times faster, primary isotope effect. If it is only 2 times faster or 1.5 times faster or 1.3 times faster, it is secondary isotope effect. Now tell me, you know what is the primary isotope effect, what is secondary isotope effect? Tell me. Should I explain it to you? No? Yes? In a primary isotope effect. Why is it called primary? What is the primary isotope effect? What is the secondary? This is the primary isotope effect. It's the secondary isotope effect.
Here the deuterium gets replaced. Here the deuterium does not get replaced with this.
Besides that,
Here it's
you tell me all sorts of differences, definitely you will get one answer. Whenever deuterium is broken in the RDS, that is the primary isotope effect. Here we are not coming anywhere in this deuterium, alpha deuterium, isn't it? But presence of deuterium will definitely, please listen, Gavaninga, a carbon bromine bond, this carbon bromine bond, would you expect any change in the bond dissociation enthalpy? Yes. Presence of deuterium will definitely make this carbon bromine bond slightly stronger. And this is related to the cleavage of carbon bromine bond. It becomes slightly difficult, it becomes easy. Therefore, the rate is going to be a difference in the rate only 2 times, anywhere between 1.1 to 2 times. That is called secondary isotope effect. But it is not involved in a reaction. Presence of deuterium is not involved in the reaction, but the presence of that will definitely have some rate difference in the rate of the reaction, because it is going to alter the bond dissociation enthalpy. Is that clear to you? And that is called secondary isotope effect. So one more IIT question, main examination question, given this and equation 2, both of them are primary, both of them are secondary. This is primary, this is secondary, this is secondary and primary. You know what's happening over here. Okay, I got another very good question for you now based on this. Tell me correctly, if you have been observing this correctly, I'll give you yet another example. All of you must be able to answer this question. Yes. Say 6 H6 plus NO2 plus to form say 6 H5 NO2, say 6 D6 plus NO2 plus C6 D5 NO2. Shall I ask you this question to you? Very simple. Both of them are primary, involve primary isotope effect. Both of them involve secondary isotope effect. This involves the primary and this involves the secondary. Or it could be secondary and primary. And one more option, none of the above. Did you say? No, no. He said to answer. Yes. Why none of the above? Because there is no hydrogen deuterium isotope effect at all. Only when you have got the hydrogen deuterium, when there is a change in the rate of the reaction, the rate of the reaction is going to be identical. We have to prove that K1 is equal to K2 here. Because the carbon deuterium bond is not broken in the rate determining step. So, that hydrogen deuterium isotope effect is the sixth point feature here that can be taken as an evidence for the mechanism. If there is a difference, how do you say it's a evidence for the mechanism? Because what do we explain by this? If a reaction, E2 reaction experiences hydrogen deuterium isotope effect, it can be taken as an evidence for E2 mechanism. How? We are proving in the mechanism carbon hydrogen bond is broken in the rate determining step. Assertion and reasoning. Assertion and reasoning. E2 reaction involves hydrogen deuterium isotope effect. Why? Because carbon hydrogen bond is broken in the rate determining step in the mechanism. Therefore, mechanism is correct. Mechanism. Quickly we will go to E1 reaction. Though there are going to be, let me write the reaction first. Please write fast. You have a beta hydrogen atom, structural requirement also. Let me write the reaction. Let me write the reaction. Double bond plus H2O plus X minus ion. Good? But not a single step process. How does the mechanism go? The base is not able to abstract, the base is not able to abstract the proton in the first step. The base is not able to abstract a proton in the first step here. It cleaves. Carbon halogen bond is cleaved, forming a carbocation. Carbon halogen bond is cleaved in the carbocation. Therefore, we are yet to cleave the carbon hydrogen bond, therefore it has to be a multi-step process. Plus OH minus N. Plus what? In fact, go ahead with the features same way. If this is clearly understood, the same features, the same order. Multi-step process, yield is less. Kinetics, nature of X, nature of Rx, and stereochemistry. Isn't it? Stereochemistry. And hydrogen deuterium isotope effect. Any one of them you can compare it. Now tell me, what should be the structural requirement for an alkyl halide to undergo E1 reaction? Why OH minus ion is not able to abstract the proton? Probably it is not that acidic in nature. Probably the carbon hydrogen bond is stronger now for various reasons. We shall see. Whenever the hydrogen atom is not that acidic, if it is not acidic, or the third one, the base used can be a very weak base, not necessarily OH minus ion. It could be any base. So when does it happen? E2 now, tell me. I should have indicated the nature of the base also as one of the features. What should be the nature of the base in E2 reaction? Moderately a stronger base. Moderately a stronger base. Here, what should be the nature of the base here? A very weak base. Therefore, it is not able to abstract a proton in the very first step here. It waits for the formation of carbocation. It remains as a spectator ion to start with, because it is not taking part. There is no collision between this. When does it collide? The moment a carbocation is formed, it starts colliding. Now what happened? It is going to abstract. Now look at this. I should have put the OH minus ion now waits the moment. Okay, the same moderately weaker base not able to abstract a proton, but how does it? Are you increasing the basic property anyhow? No. So what? Let it be polarized. Why should the same weaker base is able to abstract a proton now? Hyperconjugation. So why do you want to use it? Make use of the hyperconjugate. Tell me.
In the hyperconjugate resonance structure, you have a H plus, free H plus, and you have a double bond.
Easier answer. Easier answer. The hydrogen atom is made more acidic now. Do you accept? Tell me whether I accept. No, no, sir, I don't accept it at all. We'll have discussion on that. Tell me, I have made one statement. How many of you agree with me? The hydrogen acidity of the hydrogen atom is increased by the formation of carbocation. Raise your hand. Only one fellow has raised. Two. You also understood. The acidic, because the positive charge. What is the nature of positive? Electron deficient center or electron releasing center? Electron rich center? As an electron deficient center, what should it exhibit? Minus I effect or plus I effect? Minus I effect. Should it not withdraw the electron in this direction? If it is going to withdraw the electrons, all the adjacent bond becomes weaker. When the carbon hydrogen bond becomes weaker, don't you think the hydrogen becomes more acidic now? Isn't it?
All of those hydrogen.
Yeah, all of this. But we are interested once again, why should the focus on this hydrogen atom all along? Tell me. We have answered this question. So what?
Because 180 degrees is anti-conformation.
That this alone is going to give you anti-periplanar conformation, not the abstraction of this hydrogen atom, not this. All of them, yes, definitely. All of them. Okay? Now, therefore, so which is, when you have multi-step process, do you think both of them are going to react at the same rate? No. One is going to be slower, one is going to be faster. Now tell me, which is going to be a slower step here? In a general, I have given you the general statement earlier. In a multi-step process, which is to be identified as the slowest step? The most difficult step. Now tell me, which is the most difficult? The first one is more difficult or second one is more difficult? Accordingly, I am going to mention. No, he has other option. The second. The first one. What is there to think of? Because it involves only bond cleavage. Is bond cleavage endothermic or exothermic? Endothermic. And what has happened here? Is it exothermic or endothermic? That depends. Why should it depend? What are the various options that are happening here? Are you not forming a bond here? Bond making. Which bond is made? Oxygen-hydrogen bond. Which bond is made? Carbon-carbon pi bond is made. Which bond is broken? There is no bond. This is broken. There is a formation of hydrogen-oxygen bond. There is a cleavage of carbon-hydrogen bond. There is a formation of carbon-carbon pi bond here. Two bonds are formed, one bond is cleaved. So amount of energy given out is slightly greater. But overall reaction is going to be endothermic process. Understand? Which is difficult. Explanation number one. What is the second explanation you want to say why this is going to be a difficult process? Reactant is more stable than the product. Reactant is more stable because the product you have a positive charge. Are you going to say, I am going to keep this carbocation in this bottle now? No. Here, which is more stable? Tell me. Which is more stable? This is going to be more stable. Product is more stable. Explanation number 3. Explanation number 3. I prove that this is slow because I know, I am very sure about this second step. Second step is very fast, without doubts. Therefore, first step has to be slow. Indirect answer. Why is it fast? Why is it fast? Attraction between the charges. Electrostatic force of attraction. I told you Ag plus attracts Cl minus to form spontaneous precipitate, isn't it? Didn't I tell you that? Same way here. Then effective, the electrostatic force of attraction. Whenever there is electrostatic force of attraction, it is supposed to be. Ionic reactions are faster. Therefore, what is the conclusion? Second step is faster. I have no idea, but now I have. Since it is faster, it must be very slow. Therefore, the OH minus ion is not involved in the rate determining step. Now, I told you, we shall straight away, maybe I shall explain these to you next class in detail. Now, let us write the rate equation. What does the rate equation tell you? Now, how do you write the rate equation? By looking at the rate determining step, RDS. And rate of the reaction depends on how many species are there? Only one. Rate of the reaction depends only on alkyl halide. Should you write the OH minus ion also? No. So, what is the conclusion now? The rate of the reaction, this particular reaction, is independent of the hydroxyl ion concentration. And what do you understand from this? Independent of the reaction rate is not going to be affected. Is that clear to you? I can give you in the form of an experimental question. First experiment, 1 molar concentration, I write rate. Second experiment, 2 molar concentration, I write the rate. And third experiment, 3 molar or 0.5 molar. What should happen to the rate of the reaction? Same rate throughout, because it is not there in the rate determining step. It is found. Whenever any species is found on the rate determining step, it is involved in the rate equation. Point number 2, you have a multi-step process. You have a multi-step process. Step 1, step 2, step 3, reactant, reactant, and reactant. The first step, intermediate 1, and the intermediate 1 is going to react with this to form intermediate 2. And the intermediate 2 probably is going to react with this, some other, to form the product here. Now, if this happens to be a rate determining step, these two are not. A plus B. Let me make it much simpler to form the product. This is going to be A. Let's say first step A is converted to I1. I think I have explained it to you. The B probably is going to react with I1 to form this. The I2 is probably is going to react with C, or it could be any permutation combination. Please listen. If the first step happens to be rate determining step, B is not involved in the rate. It comes subsequent to the rate determining step. They are not to be found in the rate equation. So, what is the conclusion here? The rate of the reaction depends only on the concentration of A, independent of the concentration of B and C. Statement number 2, if this is going to be the rate determining step here, we have to include both A and B. Whatever found prior to the rate equation is also included in the rate equation. Rate equation. And it will be independent of the concentration of C. Whenever the last step happens to be rate determining step, all of them are going to be included. You are going to study all these things in detail in chemical kinetics. Therefore, E1 reaction is a stepwise process. Why should there be a stepwise process here? For the simple reason, base is not able to abstract the proton simultaneously. It waits for the formation of carbocation. And the carbocation is abstracted by the proton, but it is not there in the rate determining subsequent to that. Therefore, what is the rate equation here? To the power of 1. Let me complete this now. What is the, now you can tell me, what is the molecularity of the reaction? 1. What is the order of the reaction? It is also equal to 1 here. What is the evidence? You try to find the order based on the experiment, and prove that the mechanism that we have proposed is right. Is that clear to you? My dear students, I have taken a very important aspect of alkene and mechanism, and you must go home and revise it today itself, and whatever book you have, please go through the answers. Questions related to E1 reaction and E2 reaction, and you should be able to answer now. And any questions to be discussed, make a note of it and bring it over here. I suppose you have understood the point that here. Okay? See you. All the best. Thank you. Anuchati sir, accepting the beginning that a few spelling mistake, mathapadi one mistakes earlier. Requires some more explanation? Any point requires some more explanation? Everything was logical? Okay, good. Right. See you. All the best.